It's supposed to be up there somewhere. The right in. Hold on, I'm not there anymore. I don't know if it's on there yet or not. I just see an Explorer line. Oh, there it goes. Now it's live. Hey, there we are on Cloudy Nights.
Where?
Go to cloudynights.com homepage.
I am there.
I see you there.
Oh, there it is. That's our Zoom meeting.
Yeah.
Uh-oh, it's just me.
It's you, buddy.
Huh? Here we go.
It's a little bit of a delay on that too.
We're not going to do this full countdown, folks, because we want to start right on time. So
Okay.
let me share this.
Oh, Scotty, I'm sending you part B for tomorrow night again.
Are you? Okay.
Yeah, I just exported it. I'm gonna upload it once I'm done here with you guys.
All right.
So at 7 o'clock on the dot, you're gonna get rid of us, right?
What's that?
At 7 o'clock on the dot, we can go away,
We're going
right?
to try. Be right on time. Yes.
Okay.
You guys will want to share this as much as you can to other groups or other pages, because this is an outreach event for you guys.
Mm-hmm.
Mm-hmm.
Right. All right, I'm not seeing it on YouTube though. What happened?
Let's check something else out here.
Oh, there it is. Virtual edition.
Yep.
Is that on
There's a
YouTube now?
delay. There is a delay.
Virtual edition promo. But I see the live. I see it live. Is that coming off? That's sharing off of your screen, right?
Yep. I'm the one broadcasting it.
Okay.
And by the way, the mics are hot so they can hear you.
The people that are listening.
Yep. People that are logged in right now can hear you.
All right.
Yeah.
Welcome to the Winter
Hello,
Star
world. How are you?
Okay. And we're right at 6:45, so we got 15 minutes to talk before we start doing this. So I'm going to go ahead and take away the countdown, and we're going to go right into it.
All right.
Well, hello, everybody. I keep on wanting to say aloha because every time I go down to the Winter Star Party, I feel like I'm in warm weather like when I would go visit Hawaii. But the vibe of the Winter Star Party in the Florida Keys is different from almost any place else in the world, you know. And they say it has that Keysy feeling, you know. So that initial Keysy feeling for me is the constant dread that I might hit a key deer as I'm driving down those roads, and so I'm always really careful. But getting to, you know, I've gone to the Winter Star Party, I don't know, 20 times, something like that, and love it every time.
More than me.
I love it every time. But we have some people here that I'm going to introduce to you that are doing our pre-show, which we're just doing a few minutes before the actual event gets underway here. But we have Dr. David Levy with us, who is always has been always with me for all the global star parties we've done, and he's going to be with us through every segment of the Winter Star Party. We've got Russ Brick, who's the president of the Southern Cross Astronomical Society. And then we have Sergio Figuera. Sergio actually put together the whole Winter Star Party. So all the wonderful video editing that you're going to see, the segments and all the rest of it, Sergio did all that hard work. But David, let's get started with you for a few minutes. Normally I would do this longer, illustrious introduction that all of you deserve, but let me just say this. These are all great guys, and I love them all. And David, we'll let you take it from here.
Thank you so much, Scott. And hello, Russ and Sergio. And it's really an honor to be with the three of you today. It's very, very special. And it's also a special honor to be part of the Winter Star Party this year. It's been a number of years since I've been there, but I used to go regularly and really, really enjoyed the dark sky that would happen there. And especially in the hours before dawn, when looking to the southeast, the Southern Cross would come up. It's the only place in the United States, that one can see the Southern Cross. And I think that's really very special. And that's also not true, because I think there's maybe a place in southern Texas that you might be able to see it as well. Maybe if you sort of stand into the water a little bit and look out, you might be able to see the Southern Cross. I hope that we have a very successful Star Party this year, even though we know it will be virtual. We've really lost so much this year, but I think we've gained a few things too. The idea of having these global star parties that Scotty has arranged so professionally and well has been really very, very special and very nice to be a part of. And I've really enjoyed these events. And it's really kind of given us a different type of astronomy to enjoy. So I'm going to give a quotation for you today. And today's quote will be, and each day I will do a different quotation. Today's is from Henry David Thoreau, from his famous book Walden, published in 1854. And remember first discovering this when I was at Acadia, reading it. It was a book written over a century before, even when I did that so long ago. And I couldn't put it down. It was so special, but this is the one that I really liked. Both place and time were changed, and I dwelt nearer to those parts of the universe and to those eras in history which had most attracted me. Where I lived was as far off as many a region viewed nightly by astronomers. We are wont to imagine rare and delectable places in some remote and more celestial corner of the system, behind the constellation of Cassiopeia's chair, far from noise and disturbance. I discovered that my house actually had its site in such a withdrawn, but forever new and unprofaned part of the universe. If it were worth the while to settle in those parts near to the Pleiades or the Hyades, to Aldebaran or Altair, then I was really there, or at an equal remoteness from the life which I had left behind. Thank you, and enjoy the Star Party, and back to you, Scotty.
Thank you, David. Thank you. Russ,
Yeah.
I was talking to you earlier, and I've been in touch with both of you guys. I'll tell you from just my own experience in putting together the broadcast here. You guys made it easy. Okay, you're so organized. The production quality is incredible. So congratulations, Sergio. And I think it's wonderful that you guys kept so much the legacy videos and stuff from the speakers. I think that, frankly, I think that all of the astronomy clubs in the world should pay attention to what you guys are doing, because you do it right. And You know, when you guys see what they've put together, you're really going to feel like, you know, I mean, it's freezing here in Arkansas, and I watched it and I just kind of warmed up. So, Russ, take a couple of minutes to tell us about the virtual event and why you guys have decided to put this together.
Well, we decided to try something virtual because we didn't want to see the string of star parties interrupted. Tippy has always been the driving force, and we wanted to make sure that this year was special and that we honored him at the same time while we kept the streak alive.
Right. Well, that's great. That's great. Tippy was a good friend of mine. I'm sure he was a great friend to you, as he was to so many people. There's a scene in the video where he talks about buying shirts for 100 people, you know, 100 of his friends, and he says, "You guys didn't know that I had 100 friends, did you?" So, you know, Tippy's sense of humor was fantastic, but he did have, I'm sure he had, you know, thousands of friends over the years, and he was special to all of us, and we all miss him very much. But you guys have taken the reins of Winter Star Party. You have made it still a world-class event. If there's a top 5 group of star parties in the world, Winter Star Party's got to be in that top 5.
Well, I'm hoping it's number 1.
Number 1. That's right. That's right. Well, it is certainly number 1 in a lot of people's books, and you know, I have been to many different star parties. Really love the Winter Star Party. I keep coming back every time that I can. So, and I hope to be back in 2022. Do we already know the dates for the 2022 event, or are you guys still planning that out?
Well, we're still planning it out. We had picked, originally we had talked about the last weekend and first week in February. But the new moon actually, at the end of February, the new moon actually falls dead center in the middle of the week.
Oh.
But normally we try to keep the star party in the early part of February because it's a little cooler and it's a little less buggy.
Yeah.
Still no snow,
right.
But you know, just cooler evenings, that's all.
Right.
The skies tend to be a little clearer as well.
Mm-hmm. And I've been down there. I mean, not only clearer, but steady. The skies are so steady. Seeing conditions are world class, you know.
Without a doubt.
I've seen what I suspect was subarc second seeing at Winter Star Party. And people push their telescopes way beyond that, you know, that so-called 60 power per inch limit.
Right.
You know, and go up to like 100 power per inch or even more, you know. So it's to see Saturn like rock solid at ludicrous magnification on your telescope is a joy. So, but and then to see all the southern hemisphere objects, there's so many things that that we could talk about right now, but they're going to talk about them here in these this series of videos coming together. And I do want to ask Sergio what it was like to put the whole program together. So Sergio, why don't you say a few words?
A lot of work.
A lot of work, yes.
But we not only just put together the program like that, we also went down to Camp Wasumke, where the Winter Star Party takes place, and we recorded all our hosted segments there. So we were there introducing all the segments as they come up and stuff, and we shot a couple little fun things like the Micki's Brownies commercial. Yeah, and you know, and little stuff like that that's going to be fun. And you know, luckily I had some Micki's Brownies down there, so I was able to consume some Micki's Brownies at the Winter Star Party site this year. So
that's
that
right.
Good thing to do.
That's right. Yeah.
Well, that's outstanding, Sergio. You didn't tell me. I would have went the second day.
Ah, well, you know,
just to get a brownie.
Right. He's
Milk
holding
and
out
brownie.
I think he had like a whole plate of them. You probably just ate one or two, right?
Yeah, sure. Just like I ate one or two every night at the Winter Star Party.
Now, Sergio, you've been coming for many years. How many years have you been at Winter Star Party?
I think I started in like 2008 or 9. I can't quite remember, but that's when that's around the time that I first joined SCAS. So
yeah,
I started going out there. I had my old 10-inch Meade LX200 GPS, which back in the day you were with Meade and you helped me out with that one a few times. So
that's good.
Every time I had an issue with my scope, I'll go.
Right.
Right.
I used to go there. Back up.
And and I wouldn't have so many issues if I just read the damn instructions.
Oh, those. Well, it's no fun to read the instructions. It's better just to dive in.
Yeah.
So we've got people watching already from around the world. Lots of comments already, and so we're excited to have you join. Now, for the audience here, okay, and for all of you SCAS members that might be watching as well, okay, this is an educational outreach event. That's what Winter Star Party is all about. So you're going to want to share this as much as you can. So, subscribe to it, like it, share it, hit that little bell or whatever if you want to be notified of new SCAS programs. But you're about to see a program that is really a next level kind of thing that's coming from an astronomy club. And it's only due to the talent of the people who put this thing together, both behind the camera, in front of the camera, and in the editing room. So I'm excited to host it on our side through our computers, but I'm a big cheerleader for Winter Star Party, and I'm also glad that we were able to bring David Levy on. It's been a number of years since he's participated with Winter Star Party, so hopefully we can get David out there live when it all, when the pandemic lifts enough for us to travel and to be at these events. So, but on any account, you guys want to say anything else before we start this program?
Just, it was made with a lot of love, and I hope everybody enjoys it.
Great. Okay. All right. Well, thank you. And here we go. Here we go. Thanks, Russ.
The Southern Cross Astronomical Society welcomes you to the 2021 Winter Star Party Virtual Edition.
Hi, I'm Tim Kahn. I'm the director of the Winter Star Party, and I'd like to welcome you to our 2021 Winter Star Party Virtual Edition here at beautiful Camp Lesumke.
Unfortunately, we can't get together this year like we normally do because of COVID, but we have an amazing program lined up for you.
We will be showing content from previous years, and we also have some new speakers on tap,
as well as old material from past Winter Star Parties.
And we will also be giving away door prizes.
Being that we're doing this virtually, it gives us an opportunity to do something that we haven't done before and pay a little bit of homage to the founder of the Winter Star Party, Tippy.
We'll be showing lectures from the past. We'll also be showing videos from some of Tippy's dearest friends.
Now to kick things off, here is Tippy Dioria's 2010 opening address.
This is our 26th. How many are here for the first time? Oh, wow, that's good. Welcome. We're expecting a great week for you. We've got a lot of surprises, a lot of prizes, a lot of functions for you to do. And as you can see behind you, we have 180 degrees of southern exposure right down to the horizon. I had a fellow friend of ours, Brian White, one time took a time exposure from the berm of his telescope, and along the horizon there was a little greenish glow, and we didn't know what it was. And then we finally figured out he actually got on the photograph the lights of Havana, Cuba. They were shining there. You first-timers who's never been down this far south are in for a treat, because from here you can see objects that you can't see anywhere else in the contiguous United States. Right? You're going to see Eta Carina, of course, and our namesake, the Southern Cross.
what I'm seeing on YouTube.
Censor
is
say the Radio
still
Galaxy.
us talking.
So you got some really, really neat things to do. If you have small children, for their safety, watch out for them during observing times, especially during the daytime. The tides here go out pretty good bit, and the coral gets slippery, and we don't want any of the kids to get hurt. So watch where they're. Also, how many of you got children with them? Nobody's got children? Oh. Well, if you have children, make sure you see Marianne Feller or Claire Offerman. You can contact them through the registration desk. We have what we call the Yackers, the Young Astronomers Club. And we've got some great projects for the youngsters to do, as well as some special prizes set aside for them. So I want to make sure that we get the kids to participate. This is for everybody. It's not just for the grown-ups. Also, if you bring children to the Winter Star Party, you might want to check with Marianne about getting your child an excused absence from school, because attending this can be attributed to being an educational and science function. They might get credit for it. As most of you know about the rules and regulations at this Star Party, but however, mind, the rules are made to provide you with the best Star Party experience possible. That's why we have the rules. This is an observer Star Party, and as such, we have very strict rules on white lights after dark. If you're in an RV or tent, please make sure you have rigged it for red light. Make sure your cars, if you have to go into the car for anything, that we turn it on, or enter the car, you don't turn on bright lights. White light rule is one of the nice features of this Star Party, so don't ruin it for others. Even bright red lights are a bother. Remember, some of the astrophotographers are still using film. And film is sensitive to red light. We're currently in the backyard of Lisa and Malcolm Yapel, who are the site managers here. You can see how the place was when you arrived. It's nice and clean, the yard all mowed. It's their backyard. When we leave, we want to make it cleaner than when we got here. Also, it is my understanding that we are recycling now, so there's a recycle bin by the registration booth that you can recycle. And because we're on Girl Scout property, there are rules: no guns, alcohol, or drugs allowed. Now, I know it's going to bother the hell out of a lot of you from Miami, but also flip-flops in the shower. They pick up sand and dirt and clog up the septic system. Not something you want to have to wait for the plumber to clear. We've had problems before on the septic system with the uses of 600 people, and we do the best we can. So we just want to make sure that the only thing that goes into the toilets are your waste and toilet paper. Don't put any paper towels or sanitary napkins or any such thing like that, because it just clog it up and really make a mess of things. Also, Wednesday's snowball fight's been canceled. Tim, where's Tim? Tim's sitting back there. Tim has done a marvelous job. He took over as the director of the Winter Star Party from me, and has done nothing but a phenomenal job. He's had to come back and down, up and down the highway from Miami to solve all sorts of problems, from hurricanes and last-minute changes that he didn't know whether they're going to work or not. We have a lot of staff people. Some of them will be wearing a little green vest, or not, they'll have a badge on their sign that says staff. We're your hosts. We're not here to police you or tell you what to do and what you can't do, unless it affects, somebody else. These people are here to help you to make your stay at the Winter Star Party a memorable one. We want you to have a good memory when you leave. We want you to want to come back. They worked very hard all year. Make sure when you arrive that you check in, get set up. Make sure you get your registration in, get your door prize tickets in. We ask you to fold them so that they don't get stuck to the bottom of the drum. If you leave the card flat, sometimes it'll stick and your name might not get drawn. We don't want that. We have Lecture plans, we have, everybody's got the book, a little booklet, should have gotten it. Unfortunately, we had two of our speakers because of the launch. Russ Romanella, who is the director of the payload for the shuttle missions, got stuck with the launch yesterday, or this morning, I guess it was. It finally went off. So they couldn't make it down. So our speaker schedule got changed around a little bit. There's an addendum sheet in your program that will take care of that and give you the changes. The lectures are held in the wheelhouse, which is down here to my left, upstairs. Speed limit, good point. Speed limit on site is less than 5 miles an hour. Trust me when you see posted speed signs out on the street on the highway in Monroe County, they don't give you that 5 miles over the speed limit leeway. I know. And the tickets are expensive as hell. And if you want to keep it off your record, you got to go to driving school and you pay for that. They don't. I got a ticket for going over 25 miles an hour. Not 25 miles an hour over the speed limit. I'm not that bad, but I was doing maybe 30, maybe 5, maybe 10 miles over the speed limit. Got to take, cost me $287 and I had to go to school for 4 hours. Don't do it. We want to keep Florida green, but not with your money. Vehicular traffic up and down the roadway here, we want to be real slow, and that goes for bicycles, motorcycles, or cars, trucks, whatever we put up and down here, because people tend to walk out from behind the telescopes or walk across the street not thinking that it's a roadway, and we don't want anybody to get hurt. I'd also like, due to the circumstances of the camping areas, that any guests that are staying off site, that are not actually camping on site during the daytime, if they would park outside, it would alleviate some of the problem. We'd appreciate it. You could help out a little bit by doing that for us. And I'll close the opening remarks to settle rumor control. It's been reported to me that rumors out there that this is the last Winter Star Party. I founded this party, and if it was the last one, I'd be sure to know about it, and I don't know about it, so it ain't happening. We're going to continue on as far as I know. There's no rumors. Rumors are just rumors. So with that, Tim, did you have anything you want to add?
Yeah, Tippy, we got to interrupt you for a minute because Tim said I have to stop you, and while I'm more scared of you, he's faster than you, so.
Good afternoon, everybody. How y'all doing today? Good. Well, I'm here because I want to, on behalf of the WSP staff, we want to present a special token of our appreciation for your guidance, your insight, and you're helping us in putting out fires, okay? And, and we want you to help us continue this great tradition that we have going on here, and we cannot thank you enough. So we have a little plaque of the Valley of the Dobs. Really, these are like 50-inch steps if you look at the size of the
real big lab.
Yes, and this was made by Barry Chris Miniatures. He's here for the next couple of days, right, Charlie? Go by, see the vendors, go by, see Barry and everybody else, and have a great time here. And don't forget to see the lectures. So I believe you have a. Let me take that for you.
Please, give it to Patty or something.
Okay, and now you're going to give your presentation.
Thank you. That's too much. I created the Valley of the Dobs many years ago when we first came down here the first time. I set my 18-inch scope up right behind this podium, and we named it the Valley of the Dobs. I was so thrilled with that, I even made up some signs, not signs, but T-shirts that I made up 100 of them, and I gave them to 100 of my friends. Surprised you to think that I had 100 friends, doesn't it? And it said, I have been to the Valley of the Dobs, and I fear no evil. That was quite a surprise, and normally it's kind of hard to catch me at a loss for words. But they did it to me again.
All right, are we ready for some prizes? Aaliyah, pick a number.
243.
243, Pat. What does 243 win?
Number 243, Ian Hewitt. You've won a Power Tank Lithium Pro made by Celestron. Congratulations.
All right, guys, don't forget to get your 2021 Winter Star Party swag right here at this address.
Now, for those of you who were here, we have a recap of the 2020 Winter Star Party. And for those of you who weren't, you can see what you missed out on.
Good morning, Southern Cross 2020 Star Party from Camp Sawyer, our side of the island. We welcome you to the Boy Scout camp. You guys are great. We love having you here. Going to be another great year this year. Sitting out here on the dock where everybody's going to be swimming, hopefully. Welcome again. Glad you're here.
So this is the 36th annual Winter Star Party. I've been personally director for 18 years. We're here on about 17 acres of pristine land where we have about 600 astronomers that come from various parts of the country, and including Canada and also UK and sometimes even Australia. We have steady skies, which means that the skies are very clear, no movement of the stars when you look through the eyepiece at high powers. What I like to do astrophotography. We get to do astroimaging of the southern objects that you normally do not see from northern latitudes. We welcome you to the Winter Star Party.
I have perfect attendance. I've attended every one. Since the Everglades, the first 3 years at Mahogany Hammock in the Everglades, the next 3 years at the Boy Scout camp, Camp Sawyer, and the rest of the time here at Camp Wasumkee. I do a lot of things, but the basic job is to make sure the camp gets set up for our guests when they arrive and make sure everybody's comfortable. The thing I like about coming to the Winter Star Party is the clear skies, the steady skies, the friendships that you make throughout the years. I'm just a casual observer, so I just enjoy observing anything and everything.
We're the hosts of the world-famous Winter Star Party held in the Florida Keys every February. People come from all over the world to see our steady skies and the beautiful countryside. We have the ocean, we have southern targets that you normally can't see from the northern latitudes. Personally, I like to come down and do visual observing with a big telescope. I also dabble in some astrophotography, but I'm not quite as good as the rest of the guys, so I stick to the visual side.
It is probably my 5th or 6th Winter Star Party, and what I enjoy is having beautiful skies, and I, of course, love the people, because astronomers are the best people.
I've been coming to the Winter Star Party since 2006. Come down because I need some dark skies in the middle of winter. I have a bunch of friends I hang with, and you know, we're kind of amped for some good weather.
This is my 7th Winter Star Party. I love getting away and doing stuff like this, like a campaign, but I also love the people that you meet, the discussions you have with friends, and of course the skies aren't bad either.
This is my 5th Winter Star Party, and it's the only place I can go observing in February in shorts.
It's a nice
opportunity to get some warm weather and some outdoor activities I otherwise would not be able to experience in New Jersey.
Yeah, this is my 4th Winter Star Party. I like coming here because it's a club event for the West Jersey Astronomical Society, and I'm a member, plus you get nice warm weather in the middle of winter, plus you get 16 extra degrees of horizon, and it's addictive.
It's pretty grueling to come down here in 2 days, but it's worth it because you get to see the more southern constellations, sharing views through the telescope, and just socializing with other amateurs who I haven't seen in a long time. We get to hear speakers, have the food, so it's an all-around great time. And, you know, it's worth the 20 hours of driving.
I've been coming to the Winter Star Party since 1995. It's an annual thing for me. I wouldn't miss it. Just a great time, great people, and the observing is just incomparable. Hope we have another good one this year.
I've been coming here to the Winter Star Parties for about 5 years now. I love it here because of the weather, the dark skies, and it also gives you an opportunity to see some of my friends who come from up north, New York and Connecticut.
I've been coming here since 2007. Look me. It was minus 18 Fahrenheit when I left.
Hi, I'm Bob Mulford. I'm here from the state of Washington, the Seattle Astronomical Society, here with my sister, Karen Stanis, who lives outside of Boston. This is my 6th Winter Star Party, and it's her 5th. And we're coming here for the warm weather in February and for the wonderful southern skies and the Southern Cross and Eta Carina and all that good stuff.
Okay, it's 12 o'clock. Open the gate. Let them in.
We welcome you to the 36th Annual Winter Star Party. We hope that you enjoy your stay, and if you have any questions or concerns during the week, please let us know. And now you guys can get out of the sun.
I've been coming down here for about 25 years, and it's a very magical place where we have dark skies and amazing views of the southern hemisphere objects like Omega Centauri. I brought 2 special items with me. One is a night vision monocular along with a special eyepiece to give a maximum field of view with big telescopes. And the night vision allows you to amplify the brightness of a telescope and at the same time with filters see deep sky objects. The second is bringing the Apollo 11 eyepiece, which has an 85-degree field. That's a special 300-unit commemorative eyepiece for the fact that I worked on the program about 60 years ago. I was tasked to design the visual simulator that trained our astronauts to land on the moon on the LEM project. And it was a magical experience, and the views through the simulator is what prompted me to eventually start Teleview Optics and bring the wide field views to all of my fellow amateurs.
This is my first year here at the Winter Star Party, although Starlight Instruments has been present for a number of years now. I really like how the community engages one another, and I would hope that over the years it continues to grow. I look forward to coming back in the future.
So I'm here and with the Star Party, I'm still doing in the business a little bit helping. We came here about more than 10 years. I'd like to, everybody come by and looking for my booth.
Hey everybody, Scott Roberts here from Explore Scientific, and here we are again at the Winter Star Party. This is an amazing event. It's something I've been coming to for years and years, certainly every year of Explore Scientific since 2008. For me, this particular event is very special because I've had many great friends here, especially with Tippy, the founder of the Winter Star Party. Mike Reynolds, Don Parker, many great and iconic astronomers have been here, and you get astronomers from all over the world. So this is a very unique star party. You can see everything from giant Dobs to beautiful refractors. We come here to share with the people here and to give a door prize and to somehow pay back to the community that supports us. I tend to bring some of our larger refractors. I always bring all of our eyepieces here, and when I have something new, I bring that too. It's been a privilege to be part of this. Hope to see you here next year.
I've been coming to the Winter Star Party since I can't even remember how young I was when I first came here. And we personally have brought a 10-inch refractor that we made last year. I did the optics for the lenses. It's been really fun using the scope. I actually never get to use our own equipment, and this was a perfect opportunity this time to get to know my scope, get to know the mount, and really learn how to use it better.
So I'm here from 1996, probably first time. We've sold already 12 or 14 telescopes of this size. Whenever weather permits, it's a perfect telescope. In terms of price, it's not as perfect as others, but in terms of appearance on Winter Star Party, so it's a perfect.
Other than the astronomy, one of my favorite parts about coming here is Micki's. It's the food truck that comes here, and not only do they make the best brownies in the world, I would say they also make some of the best burgers, breakfast.
I enjoy it a lot because I meet a lot of new people from all over the world, feed them a lot of food. At all hours of the night, we're open 24/7. I make brownies. We have different kinds of sandwiches we serve them. We have a daily dinner. The brownies are all the time, 24/7, because if I don't come in here with brownies, I'm not allowed in. Everybody loves them. They sit up there and wait and hear the timer go off half the time, and when the timer goes off, they want hot brownies.
This is my first Winter Star Party, but not my first star party, so I've got something to compare it to. This one's a lot of fun. It's very friendly, lots of good people. You can't complain about the Florida weather in February, especially when you come from up north. So I came down here to do some astrophotography. It was a little windy and a little cloudy for that, but I had a great time anyway.
I'm coming to Star Party for like the first time this time. I like it here because it's south, it's warm, and I like to see southern objects that I cannot get back home, plus explore the nature around me. It's overall, it's a very good experience, no matter what the weather is.
I came here in 2004, and I didn't currently own a telescope. So I came here and I looked through basically all the telescopes in the field where I could look through them to get an idea what I was interested in actually viewing in the sky. And I had an interest in lunar planetary objects. So I had been looking through some 12.5 f8 instruments, tended to like that type of instrument, but I felt I needed a better mount. So I came up with an English yoke that somewhat breaks down and transportable, and I built that in 2005. It's good for what it does as far as lunar planetary. Every year I make some few changes to it, some improvements to it. And eventually I wanted to get it to stellophane. Love coming here, plan it every year, beautiful time.
I've been attending the Winter Star Party since the original one in 1984. The atmosphere here is unbelievable. We have a large group here on the West End that come from all over the country and now all over the world. There's a great camaraderie here. I basically look at galaxies and galaxy clusters. In fact, the night before last we looked at some galaxies that were in excess of 800 million light years away with our eyeballs, which is neat. And I take the opportunity also to do a little bit of imaging. I'm not a full-time imager, if you will. I dabble in it, and the skies here, the stability of the air is so great, and it's very dark here. It's a wonderful place to come, and you can enjoy the Keys and the water during the daytime and go to Key West and enjoy all the camaraderie available with all the astronomers here. I really recommend the Winter Star Party heartily, and as I said before, I've been coming for a long, long time.
Been coming down here every year since 2004. I like to get down here because of astronomy, a lot of things to do during the daytime, and it's nice, good weather. And it's a great bunch of people. Been coming down here with some friends, sometimes solo ever since then, and we hope to see a lot more people down here.
This is my fourth trip to the Winter Star Party, and I take my binoculars in a piece of hand-carry luggage, and 10 hours later I'm here in the Caribbean at 24 degrees north enjoying these wonderful skies. You can stay up all night observing stuff that we just can't see from back home, So everyone's pretty friendly and makes you feel very welcome, and you get to enjoy these wonderful views. And during the day, you get to enjoy this wonderful environment and chill out and relax and enjoy the sunshine.
Okay, Olivia.
186.
186. What do you think we have for number 186, Pat?
All right, number 186, Richard Sherman. You've won a Celestron Power Tank Lithium. Enjoy it.
Aloha, everybody. It's Scott Roberts and Kent Marks. Maybe we can't say aloha.
I
know, it's not Hawaii. It's the Florida Keys, and that's where the Winter Star Party happens each year. I've been to many of them. Ken has been to some.
I think 5.
5. Right. You know, it's an awesome star party, and we're glad to be part of it. We know because of the pandemic that we have to do a virtual event, but I decided to wear my hat that I wore the last time I was at Winter Star Party. And just to tell you a little bit about what's going on, we'll be here showing all of our products, and we'll talk a little bit about our door prizes. But I can't remember which Winter Star Party.
Oh,
which Winter Star Party is this?
37th.
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 Okay. All right. So we'll be back. We have lots to talk about with you, and thanks for watching.
And now here's Dr. Atta Saradejini of the FAU Physics Department with a look at the most important photos that the Hubble telescope has taken. This is really cool.
We want to welcome everybody. Not thank you, we haven't even ended yet. We're just getting started. So we want to thank everybody for joining us, and we are excited that you are here with us. I am Michael Aguinaga with the Museum of Discovery and Science. I'm the Public Programs Manager, and I am honored to have Dr. Atta Saradejini with us from Florida Atlantic University joining us today. Our topic being Hubble, and actually specifically photos that Hubble has taken, and these are some of the most important photos ever taken. And our host will go ahead and get us into those, but a little about him. First, we want to welcome all of our Leonardo da Vinci Society members to this event. In partnership with the Florida Atlantic University College of Science. So Dr. Atta Saradejini is the Dean of the Charles E. Schmidt College of Science. Before coming to FAU in January of 2017, he served as Associate Dean for Natural Sciences and Mathematics, as well as Associate Dean for Research in the College of Liberal Arts and Sciences at the University of Florida. That is a long sentence and title. Woo. Before that, he was Associate Chair and Acting Chair of the Department of Astronomy. After receiving his PhD in astronomy at Yale in 1992, he spent 7 years as a postdoctoral researcher and a Hubble Fellow at Kitt Peak National Observatory and San Francisco State University. Dr. Saradejini spent 2 years at Wesleyan University in Middleton, Connecticut as an assistant professor before moving to the University of Florida in 2001. He received an NSF Career Award in 2001, a University of Florida Research Professor Award in 2006, and was the principal investigator of a large treasury project with the Hubble Space Telescope starting in 2014. Dr. Saradejini has over 500 publications, which have over 11,000 citations. Of these publications, over 200 have appeared in the peer-reviewed literature. His Hirsch Index, according to Google Scholar, is 45. His research is focused on resolved stellar populations in local group galaxies. These include field stars, open and globular clusters in the Milky Way, M31, M33, I'm going to mess this one up, the Magellanic Clouds, thank you, and the numerous nearby dwarf galaxies. When we resolve into individual stars in these systems, we can apply our knowledge of star formation and stellar evolution to understanding the process of galaxy formation and evolution. So with that being said, I think we're going to go ahead and get started. I'm going to turn this over to Ada. Ada, take it away.
Thank you very much, Michael. That was an excellent introduction. I'm going to attempt now to share my screen. So hold your breath. And as Michael indicated, I've had a great deal of experience working with the Hubble Space Telescope. And I want to share some of that with you and talk about some of the most important photos ever taken by the Hubble Space Telescope. And as Michael indicated, I'm also a professor at Florida Atlantic University in the Department of Physics. All right, so to begin with, let's just talk about what science actually is. How do you do science? How do scientific investigations typically progress? Well, science is a tool to better understand the natural world. And it begins by taking observations. You ask a question, you take observations. Another word for observations is data. Data is meant to be understood. And so we come up with an explanation to understand what the data is saying, what it means. And another word for explanation is model, hypothesis, or theory. And every good theory makes a prediction. And predictions are then tested against the observations. If they come true, in other words, if the prediction and the observations are in accord, then the model is probably correct. If they don't, then we have to go back and change the model. And hopefully in this way, improve our understanding and our explanation of the observations and the data that we take. Now, astronomy fits into this model, or I should say this process very well of how we do science. And I want to come back to it throughout the talk and just kind of remind you of this and show you how astronomy fits into this. So this is how we do science. Now, I also want to talk about the concept of the universe as a time machine. When we look out into space, we're looking back in time. Now, why is that? Well, because the speed of light is finite, 186,000 miles per second, or 300,000 kilometers per second. So, for example, the moon, which is 284,000 miles away, is 1.5 light seconds away. The light from the moon takes 1.5 seconds to get to us. How about the sun? Well, the sun is just over 8 light minutes away. The light we see from the sun is 8 minutes old. At that speed, 1 light year is 6 trillion miles. And, you know, to our everyday experiences, that's a long way. But in the universe and in the galaxy, that's nothing. It's a very small distance when it comes to the scale of the galaxy and the universe as a whole. So when we think about looking out into space, we have to think about we're looking back in time. That means that the further away we look, the further back in time we're looking. And naturally, the fainter objects are that we're trying to study. The further away it is, the fainter it is. Obviously, it's going to be more challenging to study. But we want to look as faint as we can because that allows us to look back in time to the earliest history of the universe. Now, why is the Hubble Space Telescope so special? Well, the main thing about it is it's above the Earth's atmosphere. It's orbiting the Earth at about 350 miles, and the Earth's atmosphere is not in the way. And so the atmosphere, the blurring caused by the atmosphere is not there. It's non-existent completely. I'm going to show you some examples of what that means in a second. Plus, HST's pointing and tracking is incredibly good. As I say here on the slide, it could shine a laser beam on a dime 200 miles away and hit it exactly on the spot. That's how precise the pointing and tracking of the telescope is. And both of these factors are incredibly important when it comes to talking about the most important photos Hubble has ever taken, as I'll tell you in a second. And looking at this diagram here it's a picture of the optical assembly of the telescope. Just to go over this quickly, the light comes in from the left through the tube, bounces a couple times inside, and then ends up on the right side of the telescope where the instrument module is. And in that little box at the end of the telescope on the right is where all the instruments are, the cameras, spectrographs, polarimeters, and all those kinds of things. And then you'll see the fine guidance sensor, which I indicate here with the mouse. That is actually the box that ensures pointing and tracking of the telescope at the level that we will need it to in order to take these images that I'm going to be talking about. And of course, here's a person for the relative size. Here's some examples of ground-based pictures taken from the ground on the left compared to the same object with a Hubble Space Telescope. So at the top, it's a galaxy. On the left, you can see a ground-based image. On the right is a Hubble image. And obviously, the HST image is much sharper and easier to resolve the stars than the image on the left. On the lower part, I have a globular cluster. This is the globular cluster M15. On the left is a ground-based image. On the right is a Hubble Space Telescope image. It's not as obvious in this case, but trust me, those stars on the right are much easier to study because they're better resolved than the ones on the left on the ground-based image. This gives you an example of just how stark the contrast is between ground-based imaging and Hubble Space Telescope imaging. So that's one of the reasons why it's important that HST is above the atmosphere. Now, this graphic was released about 5 years ago when HST was celebrating its 25th anniversary. Well, this year, it's actually its 30th anniversary. It's been in orbit for 30 years, imaging the sky and taking data. And this just shows some basic information about the telescope. The most important one from our standpoint is that it's above the atmosphere, 350 miles above the Earth, and it generates about 10 terabytes of new data every year. And every single observation of the telescope ever taken is archived on the ground at basically disk drives at the Space Telescope Science Institute in Baltimore. And because all of you out there, all of you taxpayers, you paid for this, those observations are available to anybody in the world who wants to access those data. They're there. Now, moving on to what our actual topic is, which is these most important photos ever taken. And the first one is called the Hubble Deep Field. And the idea here is that a part of the sky was chosen that was apparently blank. And HST stared at this part of the sky for 10 consecutive days in 1995, took over 340 individual exposures of this part of the sky. And they were all added together to make a very, very precise, very deep observation of that part of the sky. And this shows the Big Dipper, the North Star, and that red dot is the location of the Hubble Deep Field, which was the first set of observations like this. Now, the next one shows you a little animation of where this is located in the sky. And you can see we're zooming in to what is apparently an empty part of the sky, but in reality, we see this. And so this is the first Hubble Deep Field. It was taken by HST in '95 and using what they call the Wide Field Planetary Camera 2. That's the instrument, WFPIC 2 for short. And what you see here is mostly you see galaxies. There's literally thousands of galaxies in this very small part of the sky. Everything else are stars. There's a few stars here, and you can tell the stars because they're the ones that show diffraction spikes. So for example, this is a star right here, which is a point source, but with diffraction spikes, this kind of star-like pattern, this four-pointed star-like pattern on the star itself. And there's a few stars. Here's another one over here. There's one right there that I showed earlier. There's one in the middle. There's probably a handful, maybe 10 or 12 stars in this entire image. Most of these fuzzy objects are distant galaxies. So it was a good idea, so let's do it again. So in 2003, a field was chosen in the southern hemisphere in the direction of the constellation Eridanus or Fornax. So this is a map showing the direction, the location of the Hubble Ultra Deep Field, this time in the south. And in this case, separate exposures over 4 months in 2003 were taken, hundreds of them, and combined together to form what is now called the Hubble Ultra Deep Field. And here it is. So once again, you see a lot of fuzzy objects, thousands of fuzzy objects, all of which are individual galaxies. And you see a few bright stars, again, the ones that show these diffraction spikes, the cross-like pattern which are the diffraction spikes caused by the telescope's infrastructure, and only stars show those. Everything else that's fuzzy is a galaxy. So of that Hubble ultra deep field, there was a smaller collection of exposures taken out of that that represents 2 million seconds of exposure time. And this is the extreme deep field. And this just shows you the size of the Hubble ultra deep field and the extreme deep field compared to the full moon. These are very small parts of the sky, and yet there are thousands, in some cases, tens of thousands of galaxies in these little parts of the sky. And as a reminder, each of these galaxies, these fuzzy things, is akin to our own galaxy, the Milky Way. Our galaxy contains 100 billion stars. 100 billion stars. And the galaxies you see here are between 10 times smaller to 10 times larger than our own galaxy. So what we're seeing here is literally hundreds of billions of stars right here in this one image, all organized into these fuzzy objects we call galaxies. You also notice that the galaxies come in different colors. So if you see there are some that are bluer or maybe white, say, there are some that are yellow, and there are some that are red, and there are some that are extremely red. And next I want to talk about why those galaxies are red and what that means about the universe as a whole. So here's some of those galaxies. These are, again, this is the ultra deep field, and these squares, inside each square is a galaxy, a fuzzy object. And on the right, you see kind of cutouts, thumbnail cutouts of each of those galaxies. And you can see how they all look red. Well, what does that mean? What does their color actually mean? So what they look red? What does that actually imply about the galaxy itself? And to get a better sense of that, I need to talk a little bit about the Doppler effect. This is something that's been known for a long time. And what it is, and this illustration shows that this train moving to the right, the observer over here on the right hears the train's whistle, or the sound. And when it's moving toward the observer, the train sounds like it has a higher pitch to its whistle, or its horn. Where it's moving away from the observer, it has a lower pitch. So what's happening is that the sound in the direction of motion is being compressed, and in the other direction, it's being expanded. And so the observer that the train is moving toward basically hears a higher pitch. Well, this is how sound behaves. Well, light, which is also a wave, behaves in the exact same way, in the sense that when an object is moving toward you, the light from it appears bluer than it actually is. When it's moving away from you, it appears redder than it actually is. And this is what we call redshift. And that's shown in the next slide. So here we have galaxies. So in the middle, you see from the top to the bottom, different galaxies in the sky. And then on the left, you see the light from that galaxy dispersed into its component colors. The colors are not shown here, but the blue colors are on the right, and the red are on the left. And what you see here is that from top to bottom, these are galaxies that are moving faster and faster away from us. And what happens to the light from them is the light appears redder and redder as you go from the top to the bottom. And the numbers you see there are actually in kilometers per second, which is the velocity of that galaxy moving away from us. The upshot here is that this concept of redshift has to do with the fact that when galaxies move away from us, their light becomes redder. And it's a version of the Doppler effect. In terrestrial environments, the Doppler effect is manifest in the changing of the pitch of sound, of objects moving toward and away from you. But in the galaxies in the universe, it's manifest in the redshift of the light. And what you see here then is that redshift is defined, and you don't need to worry about this math. The bottom line is that the letter Z is used to represent redshift, and the faster something is moving away from us, the redder the light appears. So that's one observational fact that we need to keep in mind. And the next observational fact is shown in this slide. And this is a plot, actually, that was made by Edwin Hubble in the 1920s. And what he found is that when he measured the velocity of galaxies moving away from us, he found that the ones further away were moving faster. And this diagram shows distance on the horizontal axis, velocity on the vertical axis, and it's a very nice straight line. And all that to say that galaxies that are further away are moving faster away from us. So in other words, the redder a galaxy appears, the further away it is. And as I show here, how red the galaxy appears indicates its distance. The redder it appears, the further away it is. And that's really just an expression of what's called Hubble's law. And what it says is that no matter what direction you look, the galaxies are moving away from us. Galaxies are moving away from us. The further away they are, the faster they're moving. And remember, when you look out into in the universe, you're looking back in time. So the further away they are, the faster they're moving. The further away they are, the further back in time you look, the faster they're moving. So that's an important point here. Now, getting back to this slide. These galaxies here are red. Why? As we just learned, because they're very far away. Their redshift is causing their light to appear red, and the redshift, how fast they're moving, is related to their distance. The redder the galaxy, the further away it is. So we're looking at some very distant galaxies. And what you notice is that these red smudges are really just smudges. They're really disorganized, kind of ugly looking things. They're not very well put together. They're kind of naughty and disorganized. And what that indicates is that galaxies that are very far away, the ones that look red, are not as well organized as the ones that are not so red and that are very nearby. And so what we can do then is kind of use this as an indicator of how galaxies look over time. And that is to say that the nearby ones look very well put together. They look spiral. They look elliptical. They're organized. They're beautiful, if you will. And the ones that are far away, the ones that are red, are less organized. They're more smudge-like. They're not as well put together. They're more disorganized. And that's really an expression of what we're finding with respect to how galaxies form, how they're put together, how they form and evolve over time. And so this picture is what's come out of some of the work with the Hubble Deep Field. And what this picture shows is on the left, we have galaxies today. So these are ellipticals and spirals today. The universe, we think, is about 13.7 billion years old. So that's why it says 14 billion years on the left. And then as you go to the right, you have 9 billion years, 5 billion years, and 2 billion years. And what you see is that as you go further back in time, and remember, we're looking very far away. The further away you look, the further back in time you're looking. And as you go further back in time, you see the galaxies look less structured, less organized. They're not as pretty, not as put together, if you will. And what this indicates is that over time, large galaxies like the Milky Way, like the spiral over there, are formed through the process of smaller galaxies coming together, colliding with each other, sticking together, and assimilating, agglomerating, if you will, into these very large galaxies like the Milky Way. So galaxy formation is a process of taking small galaxies, we call them dwarfs, and colliding them with each other. And in some cases they stick, in some cases they don't. And we're talking about hundreds, thousands of these dwarf galaxies colliding with each other to form larger galaxies like the Milky Way and the spiral and elliptical that you see on the left side of this slide. That's the process of how large galaxies form. Now, here's an example of a nearby galaxy, the Andromeda Galaxy. And it's a beautiful spiral, very well put together. It happens to be 2.2 million light years away. So the light we see from it left it 2 million years ago. But this is nearby. This is actually in our own neighborhood, our own backyard. And what you see is a very well put together, organized galaxy, but you see two nearby dwarf galaxies that are the leftovers of the process that formed this large spiral galaxy. And I just indicate them there with those ovals. These are two dwarf galaxies left over from the process of the formation, that the process that formed this galaxy, Andromeda. There were literally hundreds, thousands of these little galaxies that went into forming Andromeda, of which there's about half a dozen, well, actually more like 10 or so that are left over from that process. And that's what we're talking about in terms of dwarf galaxies coming together to form larger galaxies like the Milky Way. I should note too that Andromeda looks like the Milky Way. If you were able to photograph our own galaxy and from outside and look back on it, this is what it would look like. And we also have our own system of a couple dozen or so dwarf galaxies that are left over from the formation of our own galaxy, just like this. If we could look back on the Milky Way, it would look very similar to this picture that I show here of the Andromeda galaxy. So this slide just kind of shows what we're seeing with these deep fields. On the left, we have HST looking out into the universe. And as I said, the universe is 13.7 billion years old. And when you look nearby, that is to say, out to a few million, say, light years, those are the normal galaxies that we see nearby. And then that first magenta line is the Hubble Deep Field. That's how far back in time we are looking in terms of the Hubble Deep Field and where it looks. So that's about a billion years after the Big Bang. I can talk more about this later if you'd like, but we think the universe was formed by this very large explosion called the Big Bang, 13.7 billion years ago. And so after the Big Bang, a billion years after that is when the galaxies in the Hubble Deep Field that we see have formed and have come together. And then the Hubble Ultra Deep Field now goes back to between 0.7 and 0.4 billion years after the Big Bang. We haven't even got to the first galaxies yet, because the first galaxies are beyond the horizon, if you will, of the ultra deep field. And the first stars are even before that. And then we're getting into the early few 100 or 200 million years after the Big Bang, where we see what we call the Dark Ages and the radiation era. And of course, the Big Bang is way over to the right. So to go that extra mile to see the first galaxies is going to require, and I'll show you in a second, the next generation of space telescope. So here's what we have. So these are different ways of probing the early universe. And as I show this and discuss it, please keep in mind that as you look back, as you look out in the universe, you're looking back in time, but you're also needing to see fainter and fainter objects, because the further away it is, the fainter it is. And so the harder it is to actually observe and measure the properties of those objects. So at the top, in the 90s, we had these fairly large ground-based telescopes. And so they go back to about 6 billion years after the Big Bang. And then the Hubble Deep Field takes us to about 1 to 1.5 billion years. The Ultra Deep Field to about 800 million years. And then the next ultra deep field in the infrared, which I haven't talked about, but obviously that was the next step, to about 500 million years. And then we're looking to the James Webb Space Telescope to take us hopefully as close as we can get to the first galaxies, and hopefully, if we're lucky, the first stars that have formed. And the difference here is that the ground-based observatories, the largest ground-based telescopes now, are 10 to 11 meters across. Now, this measurement represents the size, the diameter of the primary mirror, the mirror that gathers the light from the sky. And the largest ground-based telescopes right now are about 10 meters across. Now, those are on the ground. Remember, they're contaminated and debilitated by the atmosphere. The atmosphere blurs things. So when you go above the atmosphere, you gain a lot in light gathering power for not much aperture size. So the Hubble Space Telescope is only 2.4 meters across in the size of the primary mirror. The largest ground-based telescopes are 10 meters. HST is only 2.5. And so by pushing the Hubble Space Telescope's capabilities as deeper and deeper and deeper to a greater degree, we were able to push the horizon of observations back to about 500 million years after the Big Bang. But we've pretty much reached the limit of what HST can do in terms of depth and going back in time. So the next generation James Webb Space Telescope, the primary mirror on James Webb is 6.5 meters across. So it's going to be obviously in space, above the atmosphere, and it's going to be in a different kind of orbit than HST. It's going to be able to stare at a certain part of the sky for an indefinite amount of time. HST is in a low enough orbit that the Earth actually gets in the way of the sky occasionally, and so it can't really stare at a particular part of the sky indefinitely, whereas James Webb Space Telescope can. And so with 6.5 meter mirror above the atmosphere in space, we're hoping that we're going to push the limit of what we can see back to the first galaxies, well beyond, basically well beyond where we are with the Hubble Ultra Deep Field. And again, James Webb was supposed to launch 2 years ago, but it's been delayed and further delayed, and it probably won't launch until 2021. So hopefully, when it gets up there and gets deployed, we can actually start taking some observations with it next year, maybe even 2022 if things don't go quite right. Now, this graphic just shows, kind of shows the history of the universe in a different way. And this is, unfortunately, it's a bit flipped. On the right is the present day. And as we go back in time, we're looking to the left. So the universe is 13.7 billion years old. And as you look back in time, you're seeing the earlier and earlier galaxies. And you see the first stars. And again, the dark ages. And what you're seeing here on the very left, the afterglow light pattern, that kind of colorful vertical plane, is what's left over from the Big Bang. And that's what it looks like. So this is called the primordial background radiation. And what this represents, the colors represent temperatures in the sky. The red areas are a little warmer, and the blue areas are a little cooler. But what you see here is temperature also represents density. And so what you see here are different parts of the sky that are a little warmer and a little cooler in this primordial background radiation. And I'm going to talk a little bit about what that is here. So this radiation was discovered in 1964 by these two gentlemen, Penzias and Wilson. And they used this big antenna that's behind them to actually discover this very, very, very low intensity radiation. It's all over the sky. It's called the primordial background radiation. Primordial because it was from the early universe. Background, it's all over the sky at a very low intensity. And radiation, it's a form of light. It's also called the cosmic microwave background. And so the idea is that the Big Bang happened here on the left. The universe expanded very quickly. And what you see here, this pattern of colors, is what's left over from the initial very high temperatures of the Big Bang. The Big Bang represents everything in the universe, everything you see around you, your house, your car, the building you're in, everything was scrunched, crunched down, contracted, compacted to a very, very small point. So you can imagine the Big Bang was an incredibly hot entity, incredibly hot. The universe was very hot, tens of thousands of degrees. And the Big Bang the universe expanded, it cooled off, and over time, it cooled off from thousands of degrees to what it is today, which is about 3 degrees Kelvin. Remember that absolute zero is 0 Kelvin. That's where all molecular and atomic motion stops. Well, the microwave background is at 3 Kelvin. And so We're not going to see that with HST, but what we want to do is get as far back in time as we can to the time when we can actually probe the properties of the microwave background soon after the Big Bang happened. And as I say in this slide, James Webb Space Telescope is going to help us get closer and closer to when the first galaxies and the first stars formed. So, and we can talk more about this in the Q&A session if you'd like. So these are my main takeaway points from this presentation. HST, the deep fields, the Hubble deep field and ultra deep field, they reveal the morphologies of galaxies. That is to say, how galaxies looked in the past, about 500 million years after the Big Bang. And they show that galaxies were much smaller and less organized and not as put together, let's say, as modern galaxies, the ones we see nearby that are close to us. And so what that says is that this process of galaxy formation started with many, many, many thousands, in some cases, dwarf galaxies that were orbiting each other and collided with each other, and in some cases stuck to each other. And as they stuck together, they created larger and larger galaxies like the Milky Way. And over time, galaxies like the Milky Way and Andromeda were formed through the process of these dwarf galaxies colliding with each other and creating larger galaxies like the Milky Way and Andromeda. That is the takeaway from the observations of the Hubble Deep Field and the Ultra Deep Field. I have a few more slides to show, but I'm going to just stop there and take your questions.
Okay, so I do have a few questions to ask. Are you, and then you'll show the rest of the slides? Is that what your plan is?
Well, the slides are there in case I need to use them for answering the questions.
Gotcha. Okay, so I'll start it off. The first question that we have are, what are NASA's plans for the next space telescope?
Okay. So this shows it right here. This is the James Webb Space Telescope. And as I mentioned earlier, it's going to be 6.5 meters across for the primary mirror. When we talk about telescopes, a lot of people get confused that maybe magnification is the important factor to keep in mind. But really, professional telescopes, magnification isn't important at all. It's actually the size of the primary mirror, the main mirror that gathers the light that is then studied to reveal the nature of the universe. And so the larger the primary mirror is, the more light you're able to gather, and so the fainter you can see. And the fainter you can see, the further away you can see. The further away you can see, the further back in time you can see. So those are all connected to each other. And the plans then are for James Webb Space Telescope to be launched next year, and to be in high, to be well away from the Earth, so it's not going to be obstructed by the Earth's, by the Earth itself, and so it'll be able to stare at different parts of the sky continuously, and just do many and several of these very deep fields, and hopefully get us back in time to when the first stars and the first galaxies formed. At the moment, that is really the holy grail of cosmology, which is figuring out when the first stars and galaxies formed. That's the plan.
Okay. The next question comes from one of our viewers. So it's, here it is. Are there any Z-stack photos of the universe where we can see all of these things in one image? And where to find it? And then the second kind of part to that question includes, is there any implications from any of this work?
Could you repeat that, Michael, about Z-stacked images?
Yeah, so is there any Z-stack photos of the universe where we can see all of these things in one image?
So the interesting thing about the two deep fields is one is in the north and one is in the south. They're completely different fields. So yes, you can find images, Z-stacked images of the two fields on the web. I mean, they're all over the place. That's where I found the graphics for this talk. So they're quite common. It's just that you'd have a hard time finding stacked images that are a subset of all the images taken for the deep fields. The deep fields were taken intentionally to be combined. So you're not going to find any subsets of those combined images. You'll only find the final combined image of all the images together. So that's the one limitation. But they're quite common on the web. You can easily find those stacked images.
All right, our next question is from Ivan. So would galaxies appear more blue and slow if you were near them? Also, if you could use the telescope to see billions of years away, are you able to look closely into nearer galaxies to see if there are planets and what is on them?
Right. So let me address the first one first, which is, and I'll just show this this diagram here. So this is a cartoon, really, but it is based on real data. And what you see here is that the nearest galaxies to us are moving away from us, but not at not very high velocity. Now, these velocities here, these speeds, 20, 30, 40,000 kilometers per second. I mean, to us, that seems like really fast, but it's not. The universe is actually expanding at a much faster rate than what you see here. So the nearby galaxies are not moving as fast as the ones that are further away. And clearly, it's easier to study the ones that are nearby compared to the ones that are further away. So if we want to look for planets, we want to really look at the detailed structure of galaxies. You want to look at the nearby ones, the ones that are only 10 or 20 million light years away. Those are the ones that are going to be, in other words, those are the ones right here in the very lowest distance range of this diagram. That's where you want to look for, if you were interested to do that kind of thing, to look for planets and the more distinct structure of the galaxies themselves. And there's hundreds of galaxies like that, in that distance range. But I should say that, I mean, as far as looking for planets, we've really only looked at stars in our own galaxy, the Milky Way. The Milky Way is about 100,000 light years across. 100,000 light years. That's actually pretty small on these scales. So those stars are relatively bright, and we can study them in different ways to look for planets around them. And those are really the only ones that are amenable to those kinds of studies, because the rest are just too far away at the moment, which is to say that they're just too faint. We don't have a big enough telescope yet. I should say too that this in this slide, I mentioned that the ground-based telescopes we have today, the largest are about 10 meters across, but we're currently designing telescopes that are 20, 30 to 40 meters across for the ground. These, again, this number is the diameter of the primary mirror. And the larger the primary mirror is, the more light you can gather and the fainter you can see. So the ground-based telescopes are actually trying to get as large as possible to hopefully augment some of the observations taken by the James Webb Space Telescope, that's out in space. So they're really going to be working together in many ways. But the ground observatories certainly aren't standing still. I mean, they're also extending their reach by building larger and larger telescopes with larger and larger size primary mirrors.
All right, my next question is, why doesn't gravity, which warps space and time, get in the way of these direct observations?
Okay, the reason is this, that, so let me go back to this slide here. For these really nearby galaxies, I'm sorry, I should have said parsecs is another way we measure distances. 1 parsec is 3 light years. So take these numbers and multiply them by 3 if you want to know what they are in light years. So gravity on those kinds of, at that level of effect, is really only important for the very most distant galaxies, the ones where we see their light through a lot of intervening material. The galaxies that are nearby in the hundreds or millions of light years are not actually affected greatly by gravity. Now, having said that, there are small effects that do affect the light from these galaxies. And so we know how that works. We can take those into account. As it turns out, the Einstein theory of relativity, which governs how gravity affects light, has been tested back and forth, and it passes the test every time it's been tested. And so we use our expectations from the theory of gravitation from Einstein to correct any observations we have for the effects of gravity over those very long distances. And I should note, going back to my original slide about how science works, the theory of relativity, which is what governs the effect of gravity on light, which is the explanation here, the theory. It's been tested back and forth with predictions and then with the observations so many times, and every time it's come through with flying colors. In other words, the model, the theory of gravity, the theory of relativity, the predictions it has made have been borne out by the observations and the data every time that they've been tested. So we understand gravity, or at least we think we do, very, very well on small scales and large scales. And those corrections, that understanding has helped us to, make the corrections we need to our data based on how gravity affects light. So we know how it works, and we use the theory to make corrections based on that.
All right, our next question is, how is time different in the galaxies in comparison to Earth and or our galaxy?
How is time different?
Yes.
Okay. So let me go back to this here. I'm just going to show one of these last slides here. Okay. So on the lower part of this graphic, you see time after the Big Bang. Okay. And then just above that is redshift, that Z number that I mentioned to you earlier. That's how much galaxies' light is shifted to the red. So 1, 4, 5, 6, 7, 10. And what you'll notice is that this is not a linear scale. We go from 1 to 10 in a factor of 10 between 6 billion and 480 million years. So this is not a linear scale. What this is saying is that time, while it progresses linearly, its effect on redshift is not linear. And which is to say that, if redshift increases by a factor of 2, time doesn't increase by a factor of 2. That's what I mean. And so this correlation between redshift and time is something that's built into the models, the theory of the Big Bang and how the universe has expanded and changed its properties over time. And again, this correlation is all based on this theory, the theory of how the Big Bang happened and created the universe. And going back to my scientific method, that theory has been tested back and forth in terms of its predictions and what the observations show. And so far, what we see in terms of the predictions are borne out by the observations. So that's all good. Could it be wrong in the future? Yes, of course. That's how science works. Science is a self-correcting process. And so that self-correction could take a week, 10 days, 20 days, a month. It could take years. It could take decades. But that's the way science works. It's a self-correcting process. All that to say that the model we have for how the Big Bang happened and how time progressed and how redshift was dependent on time works very well. And the predictions it makes are borne out by the observations.
Our next one comes from Mark. Are we in the middle of the universe? Why is every other galaxy going away from us?
Okay, very good question. And that's what this diagram here shows, that every galaxy is moving away from us, and the ones that are further away are moving faster. The ones that are further away are the ones that we're seeing earlier in the history of the universe, which means the universe was expanding faster in the past. Okay, that's how the Big Bang is. We think that's how it works. But it does not mean that we're actually in the center of the universe. And there is no such thing as the center of the universe. And the analogy I like to make is made by, pretty much all introductory textbooks, is that think about a loaf of raisin bread. A loaf of raisin bread, right? It's not in the oven yet, and there's raisins inside it, right? You put it in the oven, and it rises, it expands, and if you're on a raisin, you see every other raisin moving away from you. But that doesn't mean that you are in the center of this loaf of bread. So that's the analogy we like to use. Things are moving away from everything else, but that does not mean that we are at the center of the universe. And if you look at it geometrically, in terms of the models, the cosmological models, there's no such thing as the center of the universe. It's as if we're in this big raisin bread with raisins moving away from each other, but we're not in the center. So that's the best I can do for an explanation.
Our next question is, can Atta talk about why finding all these galaxies in the deep field photos are important, and what will this data be used for?
Okay, so these fields were chosen to be blank. These fields were chosen to be blank, to have nothing in them. We knew there were a few stars, but we had no idea that there were all these thousands of galaxies in these fields. And I'm just touching, this is really just the tip of the iceberg, for lack of a better term, because these observations led to enormous amounts of follow-up data taken of each of these galaxies by other telescopes. So there's surveys being done and have been done of the galaxies in these fields, all the different properties of these galaxies. And I just touched on one, which is the appearance of the galaxy and how they tell us about the formation of how galaxies come together. But there's been many, many other studies done on the individual objects in these fields and what they tell us about the galaxies and about the universe as a whole. So while this area of the sky was thought to be empty, it turns out there's thousands, if not tens of thousands of galaxies in each of these fields. The other thing I should point out is that if you looked at this is the Hubble Deep Field. And if you look at this is the Ultra Deep Field. Qualitatively, they look the same. They look the same. They have a lot of galaxies in them. They're fuzzy. They're different colors. They have a few stars, but qualitatively, they look the same. So this is the Deep Field. There's the Ultra Deep Field. They look the same. What does that tell you about the universe? Well, it tells you that no matter what direction you look north, Hubble Deep Field, you look south, the Ultra Deep Field, they look the same. The universe looks the same no matter what direction you're looking. And this is the centerpiece of two principles of cosmology. One is known as the principle of homogeneity and the principle of isotropy. Homogeneity says that the universe is smooth and homogeneous on the largest scales. Isotropy says that no matter what direction you look, you're going to get the same answer with respect to the properties of the universe. If you want to get the age of the universe, if you look in this field, the Ultra Deep Field, and this field, the Deep Field, which are in the north and south, you better get the same answer, because that's the idea. And so the fact that these two fields look the same qualitatively and quantitatively indicates that, yes, the universe is homogeneous and it's isotropic.
Next question is from Nadia. It says, for a novice astronomer who is interested in looking up at the galaxies, do you have any recommendations for which type of telescope would be best to get started with, considering the Hubble is a bit out of the budget?
Right. So Hubble is a multi-billion-dollar instrument, right? And James Webb is closer, just over 10 billion. Actually, it's probably gotten the budget overruns have probably taken it closer to 15. But I would actually just start with a cell phone app, because there's multiple apps online that you can download that will show you what this, the sky. It'll allow you to get around the sky and figure out what constellations are where the planets are, where the moon is, where interesting star clusters are and nebulae and that kind of thing. I would actually start with that. And that would be kind of the simplest, and these apps, many of them are free, the simplest way to kind of get familiar with what's up in the sky. As far as telescopes are concerned, that's a tougher one because there are so many different kinds of telescopes, designs, manufacturers, sizes. There's so many different ones. It's hard for me to give you advice here, online in this forum. I think what I would say is, look at there's two major magazines in the amateur astronomy realm, Sky and Telescope and Astronomy magazine. They come out every month. They have all kinds of ads and articles about how to buy the best telescope for your needs. There's articles online about this topic. There's all kinds of nuances to what exactly you'd like to look at, where you live, how much you're willing to spend. There's all kinds of factors. And so it's really hard for me to give you much good advice here. All I would say is that start with the app, learn your way around the sky, figure out what kinds of objects you're interested in looking at, and then do a little homework online to see what kind of telescope in terms of size and manufacture and specs are more in line with what you're interested in looking at.
Our next question is, what are you most hopeful for the John Webb Space Station to discover or confirm in the near future?
Right, good question.
Or James Webb, sorry.
That's all right. So this goes back to this slide here. I really want James Webb to see the first stars. So here they are. We're at the Hubble Ultra Deep Field. We have to go to the first galaxies and the first stars. We want to see the first dwarf galaxies coming into being and forming their first stars. Now you might ask, well, can't we see those nearby, like near the sun? The answer is yes, we can. We can see old stars near the sun. Let me just go back to this for a second. Sorry, one more here. So this diagram illustrates one more thing about the universe, and that's this. When the Big Bang started, when the Big Bang happened on the left, the universe was composed of almost exclusively hydrogen and helium. Nothing else. All the other elements, the carbons, the nitrogen, oxygen, aluminum, uranium, all that stuff was formed in stars. Now, astronomy, we're fairly naive chemists. And in astronomy, we have hydrogen, helium, and everything else. We call everything else metals. A chemist would probably be mad at me for saying that because to chemists, those are not metals. Okay. But astronomers, we call them metals because they're the ones that are formed after the Big Bang inside stars. Now, mind you, they're a very small fraction of the universe. In the sun, most of the sun is hydrogen and helium. 98% of the sun is those two elements. The rest of the sun, the 2%, are metals. Everything else, carbon, nitrogen, oxygen, aluminum, bromide, everything else on the periodic table is produced after the Big Bang. And it's a minority of the universe. But why am I talking about it? Well, because if we can find a star near the sun with very, very low amounts of metals, what that tells us is that it was formed very early in the history of the universe. That's what we're trying to do right now. That's another way to probe the earliest and first stars formed in the universe, is to look for the stars with the lowest amount of those heavier elements that we know and love in the periodic table. And so at the moment, we have actually found stars that have those heavy elements that are 1 million up to 10 million times lower than the sun's value. That's a very small amount of metals. And we think that those stars were the first ones formed after the Big Bang. But we have not found stars with zero metals yet. And that's another holy grail, if you will, in studying the early history of the universe, is stars with no metals, or basically the Big Bang fraction of metals. We haven't got there yet. but that's another direction that people are going to probe the earliest history of the universe.
Our next one is, what are the differences between the spiral galaxies and the elliptical galaxies?
Very good question. So this slide on the left, you see the two types. 90-some% of galaxies are either ellipticals or spirals. And there's, besides the obvious morphological difference, spirals have spiral arms, they're flat, they're, they have, they're flattened planes with arms. Ellipticals are round or elliptical in shape. The main difference beyond that is that elliptical galaxies are mainly contain old stars that are formed soon after the Big Bang. Spiral galaxies, on the other hand, have a range of ages in their stars. There's old stars, there are young stars, there's stars forming right now. There's regions of gas and dust where there are new stars forming as we speak in spiral galaxies. The Milky Way is a spiral galaxy, so actually the Andromeda galaxy is a spiral. And you can see here in this picture that there's all kinds of gas and dust in the disk, and kind of regions of red and kind of blue and yellow, and those are what we call H2 regions, which are areas of gas and dust that are forming new stars. And by new, I mean there are literally new stars being formed right now in this galaxy. Now, remember, when I say right now, I really mean 2 million years ago, because that's when the light we see from it left it. So, but in 2 million years is nothing in the history of the universe. So it's basically right now. So this is a spiral. Now, the two galaxies that are dwarfs that are near it are actually elliptical in their shape. So they tend to be older stars, older populations, where there's very few, if any, young stars formed in those dwarf elliptical galaxies. The main difference being ellipticals are older, they tend to be older, spirals tend to be younger in the mean.
Our next one is, if the galaxies are moving away, where are they going?
Okay, good question. So when we say galaxies are moving away from us, what we really mean is not the galaxies themselves, but space itself, the fabric of space. Einstein told us that space actually is a thing. It has structure, it has form, it expands, it contracts. When the Big Bang happened, the expansion was not of the galaxies, but of space itself. And the galaxies are attached to that space. And so when the space expands, the galaxies also expand. And so when the universe expands, it's creating space. It's not expanding into nothing. It's actually creating the space itself. And I think the best way to think about this is when you blow up a balloon. Think of the universe as the surface of the balloon. And when the balloon expands, you're actually stretching the space. It's actually getting larger and larger, stretching space, increasing the distance between galaxies. And so think about the universe as a multi-dimensional entity, and you're looking at it on 2 dimensions. And so this balloon is expanding into another dimension that we can't perceive, but we're on the surface of it. And what we perceive is this elastic space that's expanding and contracting. So that's really the way to think about the expansion of the universe, is space itself is expanding and being created, if you will, as the universe expands.
Our next question comes from, so the question is, so does this mean there are other humans walking around on these planets within these galaxies who are mirroring our lives and just like us?
The short answer to your question is yes. Yes. Look at this image. This is the ultra deep field. There's 100, so let's just say there's 1,000, 10,000 galaxies in this picture. Each galaxy is like the Milky Way. Just assume that. The Milky Way has 100 billion stars. Okay, so 100 billion stars per galaxy, and there's 1,000 galaxies here. So now you're looking at 100 billion thousand galaxies. All right, and all these stars in each of the, I'm sorry, 100 billion thousand stars, you know, in this image. And they're stars. I mean, they could have planets around them. I mean, we know from our observations of nearby stars around the sun that we've already discovered, you know, thousands of stars with planets around them. So imagine if we were able to probe our entire galaxy of 100 billion stars. Imagine how many planets could be going around those. And now expand that to all these galaxies that we see in this picture. The odds are that there is some life somewhere else around some other planet, around some other star, in some other galaxy, just given the numbers. And beyond that, it's really just a question of philosophy in terms of what you believe to be the nature of the universe. In terms of the numbers, there's plenty of probability that, yes, there are people somewhere in one of these galaxies, you know, in a planet, on a star, in a galaxy, and what in this picture, looking out in the universe from their vantage point, asking the same questions we are, and trying to hopefully get the same kinds of answers that we are. But again, it's hard to know because the only kind of life we know about is us. You know, carbon-based life has evolved on the Earth. That's all we know about. There could be other kinds of life out there. We just aren't familiar with, you know, the nature of that life. And so we're limited by obviously our own perspective of what we think life is like and what it does and how it operates. But just based on that, there's a very good probability that there are planets around these stars in these galaxies where life exists.
So somebody's taking this the other way, and I like this. So are there galaxies that are further into the future than us?
No. Okay. We cannot see into the future. We can only see into the past. And we see into the past by looking very far away. The future is being created as we speak. So there's no such thing as looking out to see the future.
Next, so although everything is moving away from us, is there any possibility of a dwarf galaxy becoming part of the Milky Way?
Yes, there is. Actually, it's happening right now. I don't have any slides for this one, but in 1994, a galaxy was discovered that was actually falling into the Milky Way right now and becoming part of the Milky Way galaxy, being assimilated, if you will, if you're a Star Trek fan, into the Milky Way. And this was a huge, I would say, tremor, you know, in the scientific landscape, because people didn't expect to be able to see this process in live action, you know, in our backyard. If you want to do a Google search on it, it's called the Sagittarius Dwarf Galaxy, and it's in the constellation of Sagittarius. The Sagittarius Dwarf Galaxy. It was discovered in 1994, and ever since then, astronomers have been trying to understand and better study its properties. Let me just quickly go to my slides and see if I have anything about this real quick. Okay, I guess I don't. But if you do a search on Sagittarius Dwarf Galaxy, it will come up. And there are many at this point, dozens actually, of dwarf galaxies orbiting the Milky Way that over time will be assimilated into the Milky Way. And if you even do a bit more Google searching, you'll find that we are actually, at the moment, flying toward the Andromeda Galaxy, this thing. The Milky Way is going to collide with Andromeda in about 2 billion years, and we're all going to be part of the same galaxy. We will combine together into one larger galaxy at that time.
Our last question, what does learning about the universe teach us about life on our planet? What will happen to our planet in the future? And will life end when the sun cools, if it ever cools?
Okay, so here's what's going to happen. The sun is about 5 billion years old. And in about another 5 billion years, it's going to run out of nuclear fuel. So the sun is powered by nuclear fusion in the very center. And nuclear fusion is an incredibly efficient process. It converts hydrogen to helium. That's what's happening in the center of the sun. But sooner or later, that fuel runs out, and that's going to happen in 5 billion years. Will we be around to, experience that? Maybe, maybe not. Who knows? But in 5 billion years, the sun's going to expand. It's going to become what we call a red giant. It's going to engulf the innermost planets. Mercury and Venus, and probably the Earth will be inside the sun. It's not going to be much fun living on the Earth at that time. I mean, every day will be a beach day. It'll be hot, right? It'll be sunny, very hot. Anyway, the point is that at that time, life on Earth will end. And that'll be pretty much close to the end of the sun's life. The sun will then have another few hundred million years or so after that before it ends its life. But that's basically the end of the Earth and the inner solar system. The other planets will be around, of course, Jupiter, Saturn, Uranus, Neptune. They'll be around to do their thing, but they'll be much different because the sun will get brighter and cooler at that time. And so the conditions on those planets and their moons will be completely different. And in the end, the sun will contract and become very small. It'll become the size of the Earth, essentially, into what we call a white dwarf, a very tightly packed, very dense object made entirely of protons, electrons, and neutrons, just basic subatomic particles. That's going to be the end state of the solar system. Now, what was the rest of your question, Michael? Was there another part at the beginning?
What does learning about the universe teach us about life on our planet?
Very good question. And I've been asked this a lot, actually. People ask, well, why do you do astronomy? What's the purpose of astronomy? And I really just have one answer, and that is, it's fun. It's fun. It teaches us about the universe. It teaches us about where we are in the grand scheme of things. It's for the sheer gathering of knowledge, the sheer application of science, and understanding and knowing our place in the universe. Now, don't get me wrong. There are some branches of astronomy that do have practical applications. We study the sun, obviously, so we know what the sun is doing. The sun's important for life on Earth. We study other planets, especially the gas giants, to better understand weather and how weather operates on large scales. So that helps us better understand weather on the Earth. But for the most part, we do astronomy for the sheer joy of gathering the knowledge and better understanding our place in the universe. And what it teaches us is that the Earth, that is a very fragile ecosystem. It's very small. It's very fragile. We look at planets like Venus, which is very hot, very, the pressure on Venus is very high. The surface temperature is 900 degrees Fahrenheit. It's very hot. Venus is a very similar, sized planet to Earth. We look at Mars, which is just outside the Earth's orbit. It's a little smaller, very thin atmosphere, basically desolate. We think there might be water on Mars, but most of it is pretty much desert. And so we conclude that these ecosystems are very fragile. And, the Earth has been around for 4.5 billion years. But over that time, the climate has changed quite a bit from cold to hot and back and forth. But it does teach us that the planetary ecosystem is quite fragile. Also, of course, look at this picture of the Andromeda Galaxy. It's a beautiful object. It's colorful. It's organized. It's a pancake. It's flat. It's beautiful. It teaches us how beautiful the universe is and how organized and how ordered it is. And it really reminds me of Carl Sagan's original series, Cosmos, which means order. And when you study the universe, you really get a sense of just how ordered everything is and how everything has been put together in kind of an amazing way in terms of how things work together. And again, that's what science does. It teaches us about the nature of the universe and how things are put together and ordered.
And now, here's a little something about Nottingham Precision Astro Engineering's Theia 90 Diagonal.
Aaliyah, I think it's time for another prize. What do you think?
Yes.
Okay, hit the button.
252.
252, another good number. Pat, what does 252 get today?
Number 252, Matt Willis. What you've won is a $200 gift card for Glider products and Starlight Instruments from Paksoon Glider. Hi, Paksoon. See you next year.
Hi, I'm Jerry Hubble, the Vice President of Engineering for Explore Scientific, and I wanted to talk to you today about the Mark Slade Remote Observatory. The Mark Slade Remote Observatory was put in service back in 2015, and Explore Scientific uses this facility to help test our products and to keep up with what's going on in the astrophotography world. The Mark Slade Remote Observatory is a fully functional remote observatory that includes a G11 mount system with PMC-8. We have the FPL 53-165 refractor in it, and also the telescope drive master that's used to precisely control the tracking rate for doing we can do very long exposures without having an auto-guiding system on it. So one of the things we do at the Mark Slade Remote Observatory as part of MSRO science is that we do cutting-edge small telescope research, which includes minor planet astrometry and photometry, exoplanet work. We do transit timings and transit work with exoplanets. We also do other types of science with the facility. So it's the final thing I wanted to say is that the MSR Science facility is available for Explore Scientific customers to try out. And all you have to do is go to our website and look under experiences, and you can find a way to sign up to use the facility and for me to personally direct you and to learn about the facility and our equipment. I appreciate your time. Thank you.
And now, Dr. Mike Reynolds talks to us about meteors in his classic presentation, Falling Stars.
Well, as some of you know, I spent 12 years as executive director of Chabot Space and Science Center and retired from that position last summer as I couldn't figure out who to vote for governor. You know, it was between, living in California, it was between either Gary Coleman and the stripper. So, well, actually she was number 7 or number 8 on the reception of votes list. That just, well, maybe she could have erased that $30 billion deficit for California, who knows. Nonetheless, another story, as is Chabot. But one of the things that I've always had an interest in, and you talk about how kids get interested in things like astronomy, in my case, or collection of rocks or meteorites and that sort of thing, are museums. And I can remember as a kid going to a museum and purchasing a little 50-cent piece of Canon Diablo and that was my very first, which I still have, my very first meteorite. And since then, I went on to do some degree work, and I love the course description, dust. Can you imagine going home and telling your wife that I'm taking a course in dust? So solar system dust and that sort of thing. But nonetheless, one of my loves, vocations as well as avocations, has been meteoritics. So this is going to be a talk that's a little different than the first two talks today. This is more of a, should we say, no pun intended, down-to-earth type of talk. And yeah, I knew that would at least wake somebody up. Thank you, thank you. I knew it would wake at least someone up. And it's interesting how all this got started for me. I've done a lot of crater research. You'll see a little bit of that work. But I've just really become a real advocate of being able to show kids and adults alike meteorites. Being a museum director, I can tell you, people love to look through telescopes and they love to touch meteorites. There's just something magical about pulling a meteorite out of your pocket and having a kid touch it. Just like it's magical to have a kid look through a telescope at the moon or Mars or Jupiter or some of these wonderful deep sky objects. There's just something that's special about that. And so it's something that kind of grew and it interested me to the point that I had a publisher a couple years ago contact me and say, hey, we know you have a good background in meteoritics. Would you mind writing a kind of a down-to-earth book on meteorites? There are a lot of really good high-level books out there, but there's not like a more current down-to-earth type of book on meteoritics. And so I wrote a book called Falling Stars and have been absolutely surprised at how well the book has been received. And the publisher, of course, is very happy about how well Falling Stars has been received. I had opportunities to travel across the country and do lectures and book signings, so it's been kind of fun. But let's get into it. We're going to talk a little bit about meteorites, meteors and meteorites first, with the lights off. Then we're going to have kind of a more of an open show and tell type session, which really one of the reasons that Tippy put me last on this schedule was to give people an opportunity more at the end to just come up and look at stuff. A lot of meteorites up here for you to look at, a lot of meteorites for you to pick up. Just don't walk away with the Martian slices, I would ask, okay? And if you, seriously, we'll talk more about things that if you may want. I know that's not the door prize, Tippy, okay? The Martian is not a door prize. But nonetheless, you'll get a chance to take a look at some things firsthand. And since it's the end of the day, you have plenty of time to mill around, ask questions, that sort of thing. So let's turn off the lights and let's talk about falling stars. Let's talk a little bit first if we go to the next slide. Let's talk a little bit first just about meteor watching. Just a real quick recap. Now, I know that probably none of you were around to see this particular shower. This was the Great Leonid Storm in 1833, a beautiful depiction that you probably have seen the artwork from this. And some of you may have seen the 66 Leonids. Let me ask a question. How many of you were fortunate enough to see the 1966 Leonids? A few of us. I was like 12 years old, and I heard there was going to be this meteor shower. It may be kind of good. And so I went outside, and I was getting only measly rates of like 5,000, 6,000 an hour. And I thought, well, this is my first meteor shower. They must all be like that. Well, you know the story. There's like my first comment was like Kiyosaki, and I thought, oh, they must all be like that. Well, of course, you find out that they're not. So anyway, let's go to the next slide, please. Meteor watching is one of the most simple, of course, of observational astronomy. You just need appropriately dressed. You need a lawn chair or chaise lounge to relax in, food and appropriate drink. You love going to meteor watches for someone just drunk out of their mind. They're facing the ground and seeing, 10,000 an hour type of thing. Not that anyone in this room has ever done that, right? Binoculars. I like keeping a pair of binoculars by my side just in case a very bright meteor or fireball bolide produces a train or a trail, so I can actually get an opportunity to observe that. Tape recorder, which can be dangerous because you may have to go through if you're going to play for your church group next Sunday and edit a few words out. And of course, dark and clear skies always do help. So we can go to the next slide, please. Just a couple types of meteor watching. We're going to spend just a little bit of time on this. Visual, you're doing things like hourly counts, magnitude estimates, duration, train, that smoke trail, etc. Telescopic, a lot of people do binocular observing of meteors, photographic, and spectroscopic. So there's some of this work that still goes on today. Next slide, please. Basically, I don't know why that came back up again. We'll go to the next slide then. We're going to make sure this is a test to see if you saw that. Okay, next slide. There we go. Now, I don't know about you, But this is like the typical observer. You're sitting there just checking out, or the thing that just hacks me off the most, you're in a group of about 10 people. You're out just kind of having an ice eating, watching, meteors. And everybody says, oh my God, and, by the time you turn this, -5 magnitude bolide is gone, and you kind of rip your neck around, you have whiplash, and yet you miss it. So that's probably the average, amateur out meteor watching. All right, next slide, please. The Leonids, of course, put on an incredible show for us in both 2001 and 2002. 2001, we had an opportunity to go about 50 miles east of San Francisco up into the foothills, and just it reminded me, not quite, but almost like the 66 Leonids, where you could actually watch the shower and watch these meteors coming out of the horizon, and then turn around like a waterfall and watch these meteors go over your head. It was just an absolute incredible experience. In 2002, Debbie and I got a chance to spend the evening or the morning, even though you had a full moon, observing the Leonids with David and Wendy Levy, and that was exciting because, there wasn't the type of activity because of moonlight you saw in 2001, but it still was neat to see this incredible show itself. Next slide, please. You've seen all these wonderful photographs of Leonids, just, an image where, just multiple streaks, and occasional, as I like to call them, UFO will wander through your field, but there's something in this particular photograph, something like about 100 meteors, 100 Leonids in that particular photo. You can't see them all. And the next one, please. It is time exposure, yes. And of course, sometimes the Leonids will leave an absolute wonderful smoke trail or train, as we refer to it as. So the Leonids put on a great show for us. Next slide, please. And so just very quickly, as you probably know, the Leonids is kind of a cool detective story. Why do we have these about 32, 33, 34-year little spikes, to say the least, in activity? It has to do, of course, with Tempel-Tuttle, the comet, where the Leonids come from. The fact that as the comet goes around the sun, the trail material has been left at different orbits. Jupiter pulls on this stuff. Successive reappearances, returns of Tempel-Tuttle create new trails. And of course, as we wham into these trails, especially the newer trails, the better shower we have. So nonetheless, it was an interesting way that I've seen that the science of meteor predictions really grow a lot during this whole Leonid scenario, as we became better and better at being able to predict not only the rates, but the time that these things would peak. And these guys were getting within minutes of actually being correct. It was a whole new level of meteor work. Next slide, please. So what we're at is 2002, of course, has come and gone. 2006, look at about 100 an hour, which is not a bad evening. It's not 10,000 or 100,000 an hour, but 100 an hour is not bad. 2007, 100 an hour. 2033, 2066, 2033, 2066, those next 33-year jumps. There will be no storms due to Jupiter again, so watch Jupiter that year instead. And the next big show we'll all be around for is 2099. Now, I mentioned these in particular because I'm going to tell you, I don't know what the reaction was. In fact, I know what the reaction was across the country. At Chabot, it's in the middle of, well, it's up in the Oakland Hills, but, light polluted San Francisco. We had to turn thousands of people away from the Science Center, from the observatory that morning in 2001 because they wanted to get up there and see the meteors. It's an opportunity for us as professional and amateur astronomers across the country to really, again, get the public involved. You know the reaction to Mars last summer. You know how the public reacts to these things. I get a little tired of hearing, that there's a lack of interest in space and astronomy in this country, yet you see these big events like this, and people just really, really enjoy it. All right, next slide, please. Let's go on and talk a little bit about meteorites themselves. We go to the next slide, please. A cute little foxtrot comic. He's out with his mitt and his mask catching falling stars. And of course, next morning he says, these meteor showers are always such a letdown. And good morning to you too. So I don't know how you try to catch your meteorites, but hopefully you have had a little bit better success than foxtrot. We can go on to the next slide, please. People always are bringing me, whether I was at Chabot or at the planetarium in Jacksonville or as a teacher, were always bringing me things they swore were, a meteorite. There are 4 major clues. One is most, not all, but most attract a magnet. The second is you have this very dark material called a fusion crust, unless it's been sitting out like in the middle of the Sahara Desert, been blasted by sand for 1,000 years. Aerodynamic shaping. Many of these meteorites have this wonderful aerodynamic shaping that show they've been through the atmosphere. And finally, this really cool thing called thumbprinting that you can really see in meteorites that show this kind of tumbling as they come through the atmosphere. My funniest story, when I was in Jacksonville, I had a man call me and he said, I swear I saw this thing hit this tree and it, like split the tree and all this other stuff. And so I said, okay, well, bring it on into me and let me take a look at it. So he brings her this piece of ugly slag. It was ugly. Not only was it ugly, it was infested with red ants. Now, last time I checked, they haven't beamed down on meteorites yet. But and I said, I hate to tell you, sir, but this is not a meteorite. This is a piece of slag, and I don't know, maybe you were drinking moonshine. And I don't know what the problem was, but this is not meteoritic. The fellow not only threatened to, let's see, I won't use any improper language in this particular thing, but the fellow basically threatened to, shall we say, take me outside and dust me off. He actually was going to have a lawyer sue me because I did not declare this a meteorite. Because what's happened, they've got these like things. There's lawyers calling now. They always catch up with you, don't they? But it's funny because, what's happened is that some meteorites go for a lot of money. We're talking about thousands. Like some of the lunar meteorites go for 10,000 to, I've even seen them as high as, hold on your seats, $100,000 a gram. A gram. And so they see these jing dollar signs, and they think, well, here's this Dr. Reynolds trying to take our big, lottery-winning space rock away from us, and, they could have the ants and rock back too. I would have even bought them a can of Raid just to get it out of my office. All right, so let me go to the next slide, please. There are 3 basic types of meteorites, well, actually 4. There are irons, stony irons, stones, and what I call meteorongs, because they ain't a meteorite, and there are just some really terrible examples out there, and people can, eBay, it's a good place if you know what you're doing, you know who you're buying from to buy meteorites. I'll tell you, almost on a weekly basis, a meteorong appears on eBay, so you need to, kind of know the stuff if you're going to buy this. All right, let's go on to the next slide, please. Talk a little bit about irons. Iron is a predominant metal. Nickel you can have between 5 and 50%, a trace of cobalt. Sounds like, someone in the kitchen cooking here. You actually have 3 major groupings based on the iron to nickel ratio. Hexahedrites, octahedrites, and this has to do actually with crystalline structure that forms in ataxites. So you can have actually 3 different groups of these iron meteorites. We go to the next slide, please. This is not how it fell. Okay, let me explain this. This is a Gibbon meteorite. And I show this for a couple reasons. First of all, this was a chunk of iron meteorite that was machined into a sphere. There was so much of this brought out of Africa in the 1990s that they made knives, they made spheres, they made wedding bands, et cetera, out of this Gibbon. And this is kind of a cool example because you can see very clearly these very fine lines called Widmanstätten, the Widmanstätten pattern. And this is something that's recognizable only in octahedrites. No earth metal does this. Only octahedrite iron meteorites. Now obviously you can see this thing is just slightly magnetic here. And it was funny, to give you an idea how this field has gone pricing-wise, which is insane. When I bought this in like 1993, I paid like $100 for it. And you think, you're insane, Reynolds, paying my wife says, you're insane paying $100 for a cue ball. This bad boy, it's about the size of a cue ball. This bad boy today goes for about $750. None of my stock has done as well as this meteorite. Now see, the lawyer's calling me again because hey, you call this a meteorite, what happened to my ant-infested piece of slag? So anyway, it's a nice sample just to show you Widmanstätten patterns, the magnetic and such as that. Next slide, please. A lot of good iron examples out there. Again, remember the idea of thumbprinting, romagolith. Look at this. You can see this beautiful thumbprinting throughout this piece of vauxhall from Australia. Just a really cool example of what I'm talking about. You can see also a little bit of oxidation. Talk about that in a moment. Next slide, please. Odessa, of course, are one of our two major craters here in the United States. Again, see the thumbprinting? Really nice thumbprinting. This meteorite, a little bit of like a fusion crust type of look, maybe a little oxidation there too. And again, if you had the chunk in front, you can see a little bit of aerodynamic shaping. Next slide, please. Sakot Alin. This is a cool meteorite because this fall occurred very recently, 1947, over Russia. And this stuff, I got some small pieces and a couple big chunks of this with me. It looks like shrapnel. But basically when this meteorite came in, it just detonated and it just sprayed the shrapnel over, producing over 100 small craters stuck in trees and all over the place. And you can really see the destructive power that this type of impact can have. So very, very, very unusual because of this sort of, should I say, shrapnel-like appearance. Next slide, please. Goose Lake. This is a cool meteorite, but this has to do with Chabot Space and Science Center, where which I directed for a number of years. This was found by a couple hunters in 1936, 1947 on the California-Oregon border. And so the director Chabot, the second director Chabot at the time, Earl Lindsley, was contacted by the Smithsonian to recover this meteorite. So they trucked in with horses and a huge wagon and hauled this sucker out. Next slide, please. Well, I tried to put this in my carry-on luggage, but it wouldn't fit. By the way, speaking of carry-on luggage, as I mentioned, I get a chance to go around and do a number of lectures on meteoritics. Have you ever tried to take a meteorite through airport security? You want a new level of challenge? Try it. The TSA just loves big iron meteorites and slices coming through their x-ray machine. There have been many a time that, well, no, it's been every time that I have been stopped hauling meteorites through airport security. I'm not going, am I going to put a, $2,000 Mars rock in my suitcase for someone to, of course they wouldn't know what it was, but you know what I'm saying, you got this little package of meteorites and, some irons and some slices and some stones, and, next thing you're doing is you're, being frisked, and, it's like, but here's my book and there are pictures of it inside of it. So anyway, it's a challenge taking this stuff through, and you too can get those nice little TSA tags. How many of you had the TSA go into your suitcase? A few of us have. Yeah, well, I tried putting meteorites in my suitcase. That made a difference. I get these little, I love it. I have a wall full of these TSA tags saying, "Dear passenger, we have gone through for security reasons and checked your suitcase to make sure you weren't carrying any, slag rocks or, well, it's just ant-infested slag rocks." All right, next slide, please. Beware of rusters. Now, this is something that I need to speak to because of a couple things. First of all, if you go out and shop for a meteorite, you'll find that there's one or two, and I think this is the right one I picked up. Again, we'll take a look at it a little bit later on, that literally will rust, will oxidize in front of your eyes. Nantan is notorious for rusting. It just literally, you can buy it, put it on your shelf, and it'll fall apart in front of you. It's very inexpensive, but there's a reason, because it's a terrible ruster. There's another one called Campo de Sio, which is, actually there's two types of Campos. There's a Campo A, or old Campo, which apparently spent a lot of time underwater, and there's a Campo B, which is a newer find they've just located, which was recovered on dry land. Be careful, because you can get a meteorite like a Nantan or Campo, old Campo, at a very cheap price, 1 or 2 or 5 cents a gram. But what you end up with is, a pile of rust, and I do not exaggerate. However, the good news is there may be a couple alternatives. A friend of mine by the name of Bill Mason has worked for years as an industrial chemist. He has background in geology. He's just developed a process for rescuing Nantans. And I got a slab, he gave me a slab of a Nantan that's been cut and preserved with his process, and it's been like this for a year, and it hasn't started falling apart yet. Now, it's interesting how he got into this. He apparently was doing some work. He did a lot of work in preserving and dealing with dinosaur bones. And so someone couldn't pay him off. They said, well, I'll send you a whole bunch of meteorites. Guess what they sent him? Nantans. So he has this whole bucket of these rusting pieces of garbage. And what am I going to do this? So what did he do? He invented a process to stop the rusting. Now, having moved back from California where it's dry to Florida where it's not, I've had to look for ways to make sure my other meteorites, my Gibeons and San Diablos and all the other irons out of my collection are not falling apart. So there's actually emitters you can now buy. Very inexpensive, a couple bucks. You put them in your cabinet or put them with your meteorite, and it just absolutely stops the rust, the oxidation in its tracks. So there are some treatments that are out there that we're still looking at, but I think that Bill's process, from what I see, if you can take a Nantan and stop the sucker from falling apart, which he has done, you may be well on your way to being able to preserve some of these things. Next, please. Stony meteorites. Interesting, over 94% of observed falls are stony meteorites. Everybody thinks they're irons because they're heavy, they're easy to identify. Nope, they're stones. Of course, we know they're from crust and mantle of asteroids. Few are theorized to be from comets. They contain approximately 75 to 90%, a fairly high number compared to the irons. Silicate materials. A number also contain nickel iron or iron nickel alloy, and you have two groups based on chondrules, these little circular things you'll see in some of the slices I have up here. Chondrites, which mean they have them, or achondrites, which means they don't. Next slide, please. This is what's known as an ordinary chondrite, Wanjing, and notice in this particular meteorite, see the fusion crust, the very black crust right there. You can even see the thumbprinting, kind of an aerodynamic shaping, the types of things I'm talking about when it comes to identifying a meteorite. Stuff really does exist. Next slide, please. Some other examples again. Notice the fusion crust here on this piece of Johnson City, very, very dark, blackish. And notice this slice. See the little bits of metal, the little metal inclusion, little shiny things. Again, the better thing, I've got examples up there. You spend some time kind of looking at some of these examples. They're very, very nice. You can see what I'm talking about firsthand. Next slide, please. Yeah, I think it's Tennessee. Yeah. Milbilili, which is, I love the Australian meteorites. The names of the Australian meteorites are the best. Camaldonga. Billy Goat Donga. I mean, there's these Cocklebiddy. I mean, they have these great names for meteorites because what they do is they name them near the closest city or region they fell. So, you know, I'm now starting my Donga collection, my Camel Donga, my Billy Goat Donga. There's a whole bunch of Donga meteorites from Australia. So, you know, some people collect really strange things, and, you know, I guess that goes beside the ant-infested slag. You put your Donga collection. All right, so Milbilili is an eucrite, a very, very rare type of meteorite, achondrite, a wonderful, wonderful fall. Next slide, please. Going to the next classification of meteorites, stony irons. You have silicates and iron-nickel mixtures in roughly equal proportion. These are absolutely beautiful meteorites. And in fact, I am going to pass one around now, and I'll get it back and I'll tell you what it's worth. This is a piece of Imelak. This is kind of the classic stony iron palisite, and there's a little box that it's in, and there's a little button on the side, so push the button, you'll see these beautiful olivine crystals within this meteorite. So you basically know that it's a pretty spectacular rock. 1% of these falls have been stony irons. The three groups, I already mentioned the palisites, which you're going to see one of Imelak, a very, very well-known Chilean fall. Mesositerites, which are kind of considered the garbage can meteorites, but are, to me, the most beautiful of all the meteorites, and Laudronites. Next slide, please. And here's another Imelak slice. This stuff is spectacular. It is just absolutely beautiful. You see these beautiful olivine crystals within this iron-nickel matrix. Just slice it. Outside they look not very pretty. Inside you slice it, they're just spectacular. You see a lot of jewelry made like this. My friend Bob Haig, who most of you know as the Meteorite Man, has actually gotten some very good quality olivine crystals out of these and had them faceted. And we worked with a man and woman last year when I was still at Chabot, who she had her wedding band made of olivine crystals. Now, very, very unusual, but quite spectacular. So, a very beautiful type of meteorite. Tells a good story, though, about the solar system, which is important. Next slide, please. This is a Saharan Fall SAH 85001. It's a mesosiderite. Again, you can see the black inclusions, the metallic sparkle. It's an absolutely spectacular meteorite. But again, tell us a little bit about the melting processes while in space. Meteorites really give us some real clues, not just asteroid and asteroid formation. Obviously, you're talking about some very rare types we'll talk about in a moment, but you also get a feel for just the formation of the solar system, the history, the age of the solar system of meteorites. They're a major, major piece of our research we do here on Earth. Next slide, please. Speaking of rare and interesting meteorites, there are some I want to show you, just some interesting things to look at. Next slide, please. You can kind of collect meteorites in what's known as micro collection. In fact, I've got a couple of my micro boxes up here. Some people complain, rightfully so, that these things have gotten really expensive. That's true. Some of the meteorites have gotten up to, like I said, I talked about some of the lunar meteorites, $10,000 a gram, which is insane. But what a lot of collectors have started doing is putting together what they call micro, or small collection of meteorites. And what I do is I usually encourage kids. You may not be able to afford the huge piece or something that's is massive, but start with something small. And that's kind of what many of us did. We went to a museum or to a rock show, and someone gave us, or we bought a little piece of a meteorite. So we instead start with micro collections. This is a selection of Chilean meteorites. In fact, this one right here is an MLAC. Now that sure doesn't look like that beautiful slice that's being passed around now, but yeah, it gives you a feel for what these smaller MLACs look like. Next slide, please. Now you want to talk about something very special. Old lovers of Mars, Dr. Parker and others of us in the room who are really interested in understanding more about Mars. These are the famous SNCs, the three major classification of Martian meteorites: Shergati, Nakhla, and Chassigny. Now, this, I wish I could say this was in my collection. If this was, I would not be here. I would be owning one of those islands off the Florida Keys. This is actually from Smithsonian's collection. Chabot had worked with the Smithsonian putting together a nice exhibit, and so when I was working with them, they said, well, would you like to see the SNCs? And these are some of the largest pieces of SNCs. You're probably looking at probably about $1 million sitting right there. Maybe a little bit more, it just depends. But it gives you a feel for the value of some of the Martian meteorites. And of course, the fun thing about this is you got to remember, Martians weren't recognized, Martian meteorites weren't recognized as so until the 1980s. We're not talking about something we've known about forever and ever and ever. We're talking about chunks that were picked up, Antarctica. People start looking at comparing them to some of the Viking data and saying, hey, it's kind of like thumbprints. This stuff's matching up. So, and we went back, of course, and you start looking at other meteorites, and voila. We found a number of these wonderful, what we call SNCC classifications of Martians. Next slide, please. Of course, probably the most famous and the most controversial this time of the Martians is ALH 84001. It's an achondrite. It's a SNCC. And this is the famous Mars rock that life might or might not have existed in at one time. And this, of course, is at the Smithsonian. It was interesting. When the Smithsonian was revamping their entire hall of gem minerals, meteorite stones, et cetera, they had 3 samples available for the public to look at. They had some odd crystal. They had the Hope Diamond, and they had ALH 84001. Of course, all the public go, oh, look at the Hope Diamond. I'm thinking to myself, if this is, and of course at that time, the controversy hadn't really bloomed that maybe these weren't little fossilized bacterial inclusions. The public understood what that really was. That made the Hope Diamond look, worthless compared to this particular meteorite. So it's interesting the public's perception. You got to admit, that's ugly. That's just not a very pretty meteorite to the untrained eye. But to some of us, like the Don Parkers of the world, the Microns of the world, others, that's looks like Donga, doesn't it? We won't go there. Okay, let's go to the next slide, please. That's in camel Donga. Okay. ALH 84001, again, this is a thin section. Just give you a feel for some of the stuff they were looking at. Next slide, please. There's the Antarctic lunar meteorite. That's a chunk And you got to understand, very little lunar meteorite, stuff that's been knocked off the moon, not by Apollo or by some Soviet spacecraft and back to the Earth. That's a huge chunk of a lunar meteorite, and there's so little of it here that it's pretty spectacular. Next slide, please. Chicken Little says, the sky is falling. Now, one of the fun things, of course, is to track meteorite falls. And of course, last year, we had this fabulous Park Forest fall outside Chicago, one of the suburbs of Chicago. And actually, I've got a Park Forest meteorite here to show you. And, you know, people weren't only collecting the meteorites, they were collecting like sections of roof that they had impacted, you know, sawing out people's roofs and stuff like that. So it's kind of interesting. Let's go to the next slide, please. I love this. And remember, graduation is not an ending, but a beginning. Yeah, it must be that ant-infested piece of slag coming in there. So anyway, let me go to the next slide, please. Speaking about impactors, you know, we obviously see craters all over the Earth. You know, obviously, we start, you know, looking at the moon, and you go back to the Earth, you see a variety of craters. We've become better and better about picking out old impact sites. It's become a kind of a fun thing. And in fact, we're turning up new craters all the time, which I'll talk a little bit about some of the research I've been doing. So next slide, please. This is a mailbox that was hit by a meteorite in Claxton, Georgia. Now, you may think, oh, that's kind of cool. Everybody's seated, right? This mailbox sold a couple years ago for $20,000. Talk about special delivery. And no wonder these people got big eyes when it comes to, you know, their ant-infested slag. $20,000 for that mailbox. But I'll do one better. Next slide, please. The Peekskill car, of course, everyone remembers the Peekskill fall. The fabulous video of this bolide coming in over the high school football game and hitting Michelle Knapp's 1972 Malibu Classic. It's probably worth about $50. She sold it for $50,000. But you can buy this car today if you'd like to. Over $200,000. So you can have a Malibu Classic for just a few dollars there. Nonetheless, can you imagine coming out and seeing this in your trunk? You know, it's like, gee, money, why me? Well, she kind of hit the lottery. Malibu Classic, I love it. She not only kept the meteorite, but she sold the meteorite. And Peekskill is a hard one to get. Usually you're paying about $20 to $25 a gram for Peekskill if you even find it. It's a tough meteorite. It wasn't a huge chunk, but it was big enough to doing the Malibu Classic. Next slide, please. And it says here that no one has been known to have been struck by a falling meteorite. Next slide. Although a dog was killed in Egypt by a meteorite years ago. Next slide. Well, they mean although a dog. This is the Nanakla fall, of course, where the story is that one dog got kind of hammered by one of the Nanakla meteorites, and it's been something that's been kind of, you know, it's just kind of a fun, very esoteric thing, but yet it's something you hear quite a bit of conversation about. Nonetheless, we know there have been strikes. You know, the obvious one is Silicon, Alabama, in 1954, I want to say, where the woman was relaxing on her couch across, by the way, from the Comet Drive-In Theater. And then came in this meteorite and ricocheted off the wall and hit her in the hip, that sort of thing. There was a young man that supposedly was pelted by a couple stones in Africa just a few years ago, and the story goes on and on. So anyway, next slide, please. One of the things I've had a good time doing is, for museum work, is doing a lot of crater research. Our own Odessa, Texas crater, which really kind of looks just like a little bit of should I say, depression. Next slide, please. Obviously, Canyon Diablo, which is tougher these days to research than it used to be in Gene Shoemaker's days, because it is kind of a commercialized place, and you know they really don't necessarily like a lot of attention to what goes on there. And next slide, please. A crater I researched twice in the last couple of years in South Africa, the Swang crater. This is only recognized as being meteoritic about 10 years ago. So we've had some opportunities to go and do some survey work, take some of the various samples of impact, and maybe even a couple samples we're having identified right now, are they truly meteoritic in nature. Now it's funny when you go out and do this crater work, obviously GPS has made it easier for us, but I still use some of the simple stuff like a big magnet. And so I can remember one of my research sites, I had my camera bag, I had this huge magnet in it, and we're saying, well, do you think there's any samples available or any samples around? We don't find anything. So I set the camera bag on the ground, and these things just go ring out of the ground on the side of my camera bag. I said, well, I think we just found the mother lode. So, so some of the simple techniques like using magnets do work. So it's not, it may not be, ant-infested slag, but nonetheless, meteorites will do for me too. So next slide, please. We look for a lot of evidence of impact. Melts, impactites, shatter cones. These are things we look at to understand when this impact occurred, how did the Earth, quote, react, unquote. And that's become a very interesting study for a number of us. Next slide, please. This is something called a shatter cone. It's from Beaverhead, Montana. And this is an evidence of impact. And it's one of these things that, again, when this great shock occurred, surrounding material basically fractured, forming these things called shatter cones. So it gives you an idea of some of the evidence. Those shatter cones are much smaller than this, but it gives you an idea of some of the evidence you can find. Next slide, please. So people often say you want more information. Some recommended books. If you want some of the classics, if you go to the next slide, please. I love Neininger's books. Find a Falling Star in Arizona's meteorite crater. Wonderful reads, very historic. Neininger was a great storyteller. He could really bring to life some of his adventures going out and collecting meteorites. It's really good stuff. Next slide, please. Dick Norton's books on meteorites. If you really want a lot of detail, chemistry, all sorts of things, Dick's books are very good. Meteorites from A to Z. I've actually got some copies here. It's a good book. In fact, the updated version is out. That if you're using something just to go through and say, okay, what type of fall, what type of find, what type of meteorite is this, how many were found, or check off on your own little collection itself, Meteorites from A to Z is kind of a fun one. Next slide. So, as I always like to say, by the way, I started saying this before Jack Horkheimer started saying. I was teaching school in the early 1970s and started saying, keep looking up, and I think I got pirated. Anyway, keep looking up. Turn on lights for a second. Let's talk a little bit about some of these other things. Where's the MLAC? Is it circulate? It's circulate. Tippy has a new door prize. It's funny. People often say, well, how much are these things worth? Are they, something that you really want to save or keep? It's just something you invest in, how crazy you can get. I just got back from Tucson, which is the big rock, gem, and mineral show. I did some book signings out there for Falling Stars. And it's always interesting to see what's new, what's the latest, what's the greatest. And of course, the big items being talked about is park forest. This is just one of the literally thousands of park forest stones that belted Chicago, the park forest suburbs. So it gives you a feel for the types of stones that you'll find. And of course, the big talk out there is the recent influx of all the Moroccan and Algerian meteorites, Northwest Africans, NWAs. There's been it's kind of been almost a flood of meteorites coming out of the Sahara Desert. And you think about this. You're walking along, there's sand, and then there's a rock. Well, guess what? That rock is most likely meteoritic. And so what's happened, the nomads, honest to God, have found out about this, and they don't even have to worry about, ant-infested slag. They're actually going out and finding literally thousands of falls in that whole Saharan desert region. And so we've been very fortunate that we've gotten a lot of really cool, kind of ordinary types of meteorites out also, but also some new, nice Martian meteorites. For example, this is a really thin slice of a basalt, Martian basaltic meteorite called DAG 476. Now, in the old day, you probably would have bought this for maybe $100 a gram. Then ALH 84001 came along, and the Martian values for Martian meteorites went from $100 a gram to $2,000 a gram. And when you go to shows, you can usually find it for about $500 to $1,000 a gram. But this is a nice Martian that you'll see. It's an achondrite, so you're not going to find achondrules within it. Just a very pretty section, little piece of Mars. And so there's some of the newer Martians up here also. I was talking about Sakota-Lin, and I'm going to go ahead and pass this around. This is that fragment, one of the like shrapnel-like pieces that I mentioned. I mean, you look at this thing, it's like a piece of shrapnel. And it's been kind of a cool find. There's a whole bunch of slices and stuff for you to come up and look at. I also mentioned the idea of preserving iron meteorites against some of these emitters that you can put with your collection. They've actually made baggies now that you can put with your collection. And I'm not up here selling these. In fact, I got information if you want to contact the guy. But I just thought that, you know, it's kind of cool. We're getting to a place now we start talking about taking. And look at this, my Nantan, I just opened up, there's already pieces of rust on the table. This is, see, anyone want meteorites? There you go, this is Nantan. It's just, you can see it's just falling apart in my hand. It's just such a terrible ruster. However, this is also Nantan. And you can see this is actually a very, I better not fall off, a very, ants, what do you know, there are ants in this piece of Nantan. A very, very stable piece of Nantan. And after he did his chemical preserving, and that, you know, that we're starting with first to be able to inhibit further rusting and take the rust out. Then it's been coated with an inhibitor to make sure that additional oxidation doesn't occur. So there may be hope for Nantan and some of the other rusters. Nice piece of Canyon Diablo. Again, you'll get a chance to come and look at some big slabs and different types of samples and that sort of thing. Yes, go to the questions. Tippy?
I've got some meteorites that are sliced and what can I do
if you have small amounts, you know, there are people, I've actually done some, so we can talk afterwards, but there are people who do that sort of thing. See, Lori keeps on calling me. I tell you, they're after my, you can talk to me and we can either hook me up with me or some others can do it. Oh, okay. Well, you know, on Wheel of Fortune, you know, he has Vanna White. Well, I'm even better than that. I've got Debbie Reynolds. The true famous one in my family, my wife. But nonetheless, it's been kind of fun. Say hello for me too, Don, okay, will you? Okay. It's my lawyer. It's calling Don now. Nonetheless, I did bring some copies, and my publisher loves to send me out on talks. I did bring some copies of Falling Stars. And when I went out and started doing book signings, it was funny because everybody kept on saying, well, aren't you selling meteorites? I said, no, because I've written a book. You can go somewhere else and buy meteorites. So what I did I did at the Astronomical League convention last summer. I brought some small pieces along. So when I was out in Tucson, I brought back a whole bunch of different types of meteorites. If you're interested in buying some, you could buy one of everything, the smallest amount, and pay $35. You could buy one of everything, the biggest pieces I have, and pay $325. So there's a whole variety of Ben Sauer, which has a nice little fusion crust, to Sakota-Lin, some small, mostly small stuff. If you want bigger stuff, you know, go see Bob or others or talk to me. If you say, I want to buy some meteorites, and tell me some of your favorite dealers, I'll be glad to put you and give you their names. I mean, I don't get a cut out of this. I just have people I deal with when I buy some of the bigger samples. I'm doing research or for the museum. And ones at Chabot, I buy meteorites for Chabot all the time. And so it's you get to know people, and people you know you're going to get a good price or dependable or a good slice that's not going to fall apart. But even with stones, I mean, you can get a big slab like this guy here. This is from one stone that was about 82 kilograms, and so it had been sliced. I mean, you got to make sure even slabs like this that they're not cracked and they're going to fall apart. Someone may sell it to you for a good price, but it turns out to be like an Nantan, too good to be true price. So if you're interested, talk to me. Pick up my card. I have some business cards. I have some business cards up here, and drop me an email. It's pretty easy. It's astrogator90@aol.com. I'm at the University of Florida, so, okay, all you Seminole and Hurricane fans in the room, you'll have to forgive me that AstroGator. So, anyway, astrogator90@aol.com. I got some business cards. You can pick those up. And we're going to be up here. Debbie's going to set up some meteorites and books for sale. I'll be here to talk about this. I'm even willing to scrawl an X on a book if someone wants an autograph. And we'll open it for questions. Otherwise, I'm going to let you come up and wander. The reason Tippy put me in today so people have time to come and look at the stuff, and we'll go from there. Questions? Guess that means no.
Time for another drawing.
153.
153, Pat. 153, Pat. Give him a prize.
Number 153, Pete Wessels. You've won a Teleview 13mm Nagler Type 6. Hi, Uncle Al. See you next year, we hope.
Let's spend a few minutes with Explore Scientific and their amazing line of products.
These are Explore Scientific's truss tube Dobsonians. We have a 10-inch f4.5, a 12-inch f5, a 16-inch f4.5, and this massive 20-inch f3.6. All of these telescopes can be completely folded down so they'll fit in the back seat of a small vehicle. So you can take them anywhere. We do recommend for the 16 and the 20 to have somebody help you lift it out of the car because a lot of optical weight there. So let's go over some of the features. We're going to talk about the 2-inch 2-speed focusers on which models again, Kent?
The 2-inch 2-speed focusers come on the 10-inch, the 12-inch, and the 16-inch.
How about this one?
The 20-inch comes with a 2.5-inch 2-speed focuser. Rack and pinion, they're all rack and pinion focusers.
So real smooth, right?
Real smooth.
Real smooth. Now, also these telescopes have large oversized bearings, okay, so that you got a real smooth adjustment for every Dobsonian needs. We captured the knobs so that you don't lose knobs out in the field. But let's talk about some of the other features. How about collimation?
Collimation of a big Dobsonian, any Dobsonian really is tough because you have to have two people. This design includes this little tool right here, which is very simple to put down into the focuser.
Yes, our magic wand.
Into the focuser. Into the secondary, the magic wand.
Yes.
And collimate the telescope by yourself.
By yourself.
Which is huge.
That's the magic.
Additionally, they come with counterweight as accessories. You need counterweights, and they come with a in and out fan so you can get your mirror cooled down to ambient temperature.
That's right. So it comes with a little battery pack as well. You'll also get a shield that will block out stray light from the eyepiece cage area.
Next, we have Charlie Warren, who is the editor-in-chief of Amateur Astronomy magazine. He will be doing a presentation on astronomical outreach and the history of the magazine as well.
So this afternoon I'll talk a little bit about amateur astronomy, my involvement with it, the magazine that I publish. But the main thing, or the main focus, is I really think that amateur astronomy is important in the context of our current culture, and I'll explain that as we go through. The 25 years happens to coincide, interestingly, our magazine's been published for 25 years. That was, even though I was not the founding editor, that's when I got my first serious telescope as an adult, and they happened to correspond that same year, just pure coincidence. And the beautiful questions is what we'll get into. First, when I took over from Tom Clark was the founding editor, and I took it over in 2006. First thing I did was digitized all the back issues, which we make available, so you can catch up. And we've got actually now a thumb drive comes with 100 issues on it, and also allowed me to go in color. As small press, you have to make some trade-offs somewhere, and I did not want to go to tissue paper thin. I like high quality paper, high gloss, and most of our content fares pretty well, but there is some stuff that specifically goes digital. And the other thing was, it's becoming extremely expensive to mail overseas, and I wanted to give some options, and so it's expanded our reach a great deal. This week, don't ask me why, out of the blue, we got like 5 new subscriptions from South Korea, you know, of course digital. So that stuff happens, but this talk kind of came out of that. So going back to what got Tom Clark started on this. He was a woodworker, he was a machinist, and he built Tektron telescopes, and I still run into some of them on the field. And these were his two favorite publications. Deep Sky, published by David Eicher, who is now the current editor of Astronomy magazine. And after a while, he stopped publishing, and Telescope Making, because Tom was a visual observer and he loved making telescopes, so guess what? These fit the bill. And Telescope Making was published by Richard Berry, who, interestingly, is the ex-editor or former editor of Astronomy magazine. And both of these gentlemen really have been great supporters of the magazine. They actually purchase subscriptions, which in this industry usually there's a trade-off. So I appreciate their ongoing support. But when they stopped publishing, Tom was waiting for somebody to pick up the pieces, and they waited around, nobody did anything, so here he goes, Tom Clark, spring 1994, whopping 34 pages. Put it on and organized a trip, went down to Australia and wrote about it. And his, of course, what he does, if you look at the cover, it bears a lot of resemblance to those two former magazines, because they made a big impression on him. And he actually stole some of the authors from those previous publications, including, go back to that beginning one, Sue French. She actually got launched as somebody writing, contributing articles, and we cover some of her stuff in the early issues. So from there, we went on, and again, I've kind of updated it a little bit, expanded it. Now our print publication runs 72 pages, and our digital usually runs somewhere between 85, 100 pages or something like that. A little bit different expanded content, and there's some additional stuff that we can cover as well. I also made like I said, the back issues all available in PDF format, so people can travel with them, and it gives them a little bit more flexibility. So in the process of doing all this, you expose yourself to the public, which always results in interesting critiques and criticisms. Just comes part and parcel of package. But here we're interesting. I'm out there kind of getting out the good news about amateur astronomy at the Northeast Astronomical Forum. Great event. And in the booth, help me out, is one of our younger subscribers. I know sometimes people think that there's nobody young in this hobby. Not true, and I'll share that a little bit. But Julia Mariani is currently a dual major at Brown University, majoring in physics and communications, dual major. She wants to be the next Carl Sagan, and knowing the young lady, it's very possible she will be. And in front of there is somebody who's subscribed since our very first issue, and we're really pretty blessed to have a lot of those people that have stayed with us for a very long time. Well, you can see here with my Starship Trooper helmet. There was an event, like I say, when you're out there in the public, you get some interesting stories. So I was at Neve behind the booth, and Saturdays are just crazy. And I'm going along, and I see this guy heading towards me with a very determined look. The head is about 2 feet in front of his feet as he's marching towards me. So I thought I would break the tension a little bit. I was doing a skit later, so I put on the Starship Trooper helmet. Figured it would break the mood a little bit, and if nothing else, divert a head blow. So he comes up to the booth, and he looks at me, and he says, this is the most interesting critique I've read. I hate the name of your magazine. Now, I've had people say they hate the magazine, they hate me, they think I stink, but hate the name of, so I thought, okay, we're here in an amateur astronomy event. I looked back to make sure the banner said what I thought it did, and truly I was nonplussed. So, okay, at this point I figure it's safe, no head blow, so I took off the helmet and said, what is it that bothers you about the name of my magazine? I mean, I truly couldn't figure this one out, because I hate that word amateur. And then he launched in this whole thing about all the incredible things that amateur astronomers are doing, their contributions to science, the different things he had, variable observing. And I'm nodding my head, yeah, we cover that. So, yeah, that's great. That's good stuff. And then at the end, so that's why I hate amateur. And I said, well, let me ask you, is anybody paying you for your astronomy pursuits? And he just looked at me for a minute, made me regret taking off the helmet momentarily. And then just turned around, marched off, didn't say anything. And I was like, Okay, maybe I could have been more subtle for that, but at the end of the day, we have subscribers who truly are professional astronomers. Most of our people are engaged in this in the traditional sense of the word because they love what it is. It's a hobby that they are pursuing because of their interest as an amateur, unpaid basis. So, but it does remind me of somebody I got together with, a professional astronomer, and Rob McNaught. When I was down in Australia, I had the good pleasure of spending an evening comet hunting with Rob McNaught. And there are a couple of surprises. One thing that I didn't realize comet hunting had as much to do with the rugby watching. I mean, that was kind of interesting. A lot of rugby watching as he's comet hunting, because a lot of it's automated stuff. But it was great to spend time with him. Interesting fellow. And he was mentioning that he was getting ready to go on vacation. And I asked him about that, doing anything astronomy related. No. So my logical thing was, hey, do you ever regret moving from amateur to professional basis? And he thought about it for a minute, and he goes, no, I think it's better to be paid to search for comets than not being paid to search for comets. And impeccable logic, hard to argue with that. So anyway, I'll tell you, if you can see this, this is an image I took about 6 years ago at the Winter Star Party. The crescent moon was rising, the Milky Way, can't see very well. But this is our campus here. Beautiful place to have a star party. And my background, how I got involved, my educational background, electrical engineering, dual music major. So my life sometimes is like, some people have a well planned out life. Mine's a little bit like dropping a stick in a flood tide stream and, bouncing off rocks, and I'm here, there, everywhere. But I've always had a fun time. My wife says it's never been boring anyway. But it does go back to early experiences I had. I actually grew up here in Miami. Anybody familiar with Dinner Key Marina? Lived on a boat there, and went to school, Coconut Grove, a little private school called Ransom, now Ransom Everglades, where my dad was a teacher. I had the good fortune I could hop in my little boat and go to school. Nice way to grow up. Trying to get back to that lifestyle, actually. But we lived on a boat there, and being a teacher, he had the summers off. So we'd cast off the lines. We'd cruise in the Bahamas and Virgin Islands every year. Again, like I say, trying to get back to that lifestyle. It's like, you know what, I gave up. But I did appreciate it. But back then, they didn't have GPS. There was no GPS, so we had to do it the old-fashioned way. And that was my first introduction to the celestial mechanics. So we'd actually use one of those things called a sextant, housed in this black walnut box with the green velvet. It's kind of a magical tool. And we had the big, ship's compass and ship's chronometer, and we had beautiful charts that we'd lay out. And that's how you charted your course. My dad was an Air Force navigator, so pretty good at it. He taught us how to do it. And when we were in the Bahamas, it's very different than what is there today. They weren't cruise ships owning these islands. They were uninhabited except for lighthouse keepers. And they had the most beautiful dark skies. And we couldn't afford to run the generator, so we had to survive just fishing and diving and sailing all day. So at night you're pretty tired anyway, but we'd lie on deck every night. My dad would usually read a little bit to us, and then we look up the stars, and Mom would teach us the different stars she knew, the constellations, and Dad would fill in with some the mythology behind it, which I think he elaborated on quite a bit for general entertainment purposes. But it was a magical experience, and at the end of each summer we got to enjoy the Perseid meteor shower. Still my favorite, and usually one of the more dependable ones. And I got to tell you, when you're sitting at anchor in an uninhabited cay in the Bahamas, beautiful pitch black skies, and you see a meteor shower and a bolide rip across reflected in the water, it's truly a magical thing. And it made a real emotional impact on me. It's one of those things that's like, wow, can I get back to that experience? And like most people, things get in the way, life, keeping a roof over your head, 3 square meals. And so a lot of years went by before I returned and got to get back into astronomy and got to enjoy dark skies like I enjoyed as a kid. And when I went to Dallas, Texas, I was working for actually Brinks Home Security in their corporate office there. And Margie bought me, I had a telescope all this time, used it some, but she bought me a little go-to telescope that actually let me enjoy in the suburbs. And I was like, and I joined the Dallas Astronomy Club. And they invited me, you got to come to Texas Star Party. So in year 2000, that was my first dark sky star party. And the skies were phenomenal that year, as it would be, happened. You know, sometimes it works with you, sometimes it doesn't. This was a true sleep deprivation type of experience. It was wonderful. Anyway, so I was on fire after that. I met some people out there. They were doing some digital photography. I figured the film thing wasn't for me. I tried the hand guiding and just, I'm not patient enough. But Gary Honus I brought out a monoscope. I spent a lot of the time looking through a 20-inch Starmaster, and it was wonderful. Well, following that, I got more involved in the local groups, and somebody called me one night and said, hey, Charlie, we've got a group of people. We're going to put together 12 people, and we're going to rent the 82-inch McDonald Observatory telescope, new moon night. This doesn't happen that often, all night. And I didn't have to check my calendar, because anything, I don't care if it was, you know, a in-law's wedding, it wasn't going to happen. I was going to go. So I said, yeah, put me down, chalked up $100, $100, best $100 I've ever spent in my life, I think. Well, we got out there, and you know, what you see is what you get out there in clouds and everything else. You rent the scope. There's no, like, you know, pass on it. Right as the sun went down, the sky opens up, beautiful. We got like 9 hours of observing in on that scope, which is just phenomenal. When we, at the end, we knew we were going to ruin dark adaptation. When we put that thing at 832x on Saturn, the Yankee division looked like a NASCAR track. And the first guy that went up to it, it looked like somebody shone a high beam flashlight on his forehead as he's approaching it. I said, this is going to be good, but this is going to be the end of our observing. So, that was my first article for amateur astronomy. I contributed with Tom Clark at the helm, and of course led to some other things. But that experience really got me involved in the hobby in a deeper way. I was total immersion at this point. But it left me with that and following long, late nights, sometimes dark, hot nights, takes and has an ill effect. And so I ended up with this diagnosed with OAAD. And you know, if you all have been out there doing this stuff, there's no cure. So just in case you have it and you haven't had it properly diagnosed, so you might have obsessive amateur astronomy disorder, if follow Jeff Foxworthy. So, if you think $20,000 is an outrageous sum of money to remodel your kitchen, but you think it's perfectly reasonable to spend that much on a telescope, you definitely have the symptoms. So you drive something like this on the left during the day, so you can drive something like that on the right? Right. Yeah, you got it. So your idea of a great vacation, and you guys can definitely identify with this, hang out in remote dark skies with limited creature comforts, with a bunch of other people, you know, sweating in the heat and the cold, you got bugs, sleeping in close proximity to a portalet, and that's a great time. Then you definitely have OAAD. You walk around your house with a patch over your observing eye to protect your dark adaptation. You definitely have some issues. So, and you've got more eyepieces than you or your spouse have shoes. And you notice here, Miss Aguilera, I just noticed after the fact, but look in the back there. See the eye patch? She's a closet astronomer, I'm certain. So. And this is an actual friend. Your living room looked like this, while simultaneously his dark area for his observatory looked like that, very well appointed. So you notice where the priorities are. The sun's sitting in a folding chair. So your backyard looks like this. You lost your kids 3 days ago back there somewhere, but all you can talk about is your nitrogen purge cooling system on your telescope. You definitely have the symptoms. You look at the forecast, you see these little suns and the clear sky, and it makes you deliriously happy. But you see those little cloud icons and you get depressed. You got it. Everybody that knows you, your friends, your co-workers, they have these names: Astro Nerd, Space Cadet, Captain Kirk, whatever. And you like it. That's it. You got it. So they call you Mooney, Moonchild. That has nothing to do with either of these two things. Then could be. Some of you don't remember back in the days of the Moonies, but all right. So we're definitely different. There's no question about that. And there is a reason for it. Even if you have just rudimentary information about this hobby, you are different than the average person. They did a survey, and honestly, I couldn't believe it. 25% of the people are still confused about whether the Earth travels around the sun or the sun around the Earth. 25%. That's, I mean, pretty shocking. So yeah, Randy's like, obviously not into solar astronomy. Yeah, we're different creatures. And there was a talk show host discussing with two educated guests, and they were discussing, is the moon a star or is it a planet? So, I mean, and this was a real discussion. So even rudimentary information, you guys have more information. You're different from the general populace. So, got to understand that. And I'm sure, how many people here have had somebody confuse and say that you've had an interest in astrology? Yeah, big confusion. I mean, they did have common roots a couple of millennia ago, but they have parted ways. And so here's, I thought, an interesting meme, and on the left there, you know, your relatives, sometimes they don't know. They think you see through a telescope what they see in a Hubble space image. And my family, really, I've had family members that ask me and say, hey, they read about exoplanets. Can you see one of those exoplanets? It's like, no, my God, I need a little bigger budget for the scope. My neighbors are pretty sure this is what I do with my telescope. You know? I actually have a story about that. My wife doesn't think it was funny. I thought it was kind of funny. But new neighbors just moved in. I had my 20-inch Dob out there, and I was aligning a finder scope on the thing. Well, I mean, you know, first, they don't look like they're, most people, if they don't know, the idea of a telescope is the low refractor or something like that. That's a normal scope, not this thing that looks like it launches bombs or something. So I'm getting it lined up, and the top of their chimney just happened to be a, you know, we're in a cul-de-sac, pretty big place, so that's far enough away I could start to align it. Well, I'm there, and these people had just moved in, and as blind down, come down, and this lady comes out, and she stands on the front porch just looking at me like this, you know, with the hands on the hips. I recognized it, you know. Didn't have my Star Trooper helmet, so I'm like, I wasn't quite sure. I waved, you know, friendly. Hey, neighbor, you know. Just turned around, went back in. So kind of like the other guy. I was like, okay, I didn't make a favorable impression. And then I saw other blinds going down, and I thought, I looked at the scope, looked at the house, and thought, if you don't know better, this is probably what you're thinking. So I told my wife, and I thought it was pretty funny. She didn't think it was funny at all. You go over there and explain. I go, no, we'll let them sit on it for a bit. Anyway, professionals think we see absolutely nothing. We kind of tend to apply inverted imagination, and what we really see is somewhere in between. But what we know really does impact how and what we see as well. And then there's the star party thing. I mean, if you're still working, or if you've got friends or neighbors, hey, what are you doing on vacation? We're going to a star party. And what star are you looking at? I mean, if they don't know, do you have moon parties? They have planet parties? So is it, they get you vote which one you're looking at. So they don't know. You know, some of them think that somewhere between Nostradamus and Copernicus is what you're doing. My family thinks that's what I'm doing. And I must say, some of my friends reinforce that myth of, you know, kind of the party part of it. My neighbors, you know, based on that, they're always thinking the best. So that's what they think. And the professional astronomers think we play with our little toys. We think that we're using our huge scientific instruments, and what we really do is hang out on a field with like-minded people who also have a passion for astronomy, and it is a great time. It's a great time to explore other pieces of equipment, find out what other people are doing. So, and I just include this. So we talked about the astrology thing. These are the people that print my magazine, have printed my magazine for 7 years, and here's the notice. Inside notice, created job, 2019 amateur astrology. These are people who print my magazine for customer amateur astronomy. It's like, so I mean, I've been introduced, and it's even more serious for me. You know, Charlie has a deep abiding interest in astrology, and you see the person withdraw their hand, think you're going to do a palm reading or something, or you get the other one. Well, it's even worse when they say I publish an astrology magazine. Now you're like a different kind of person. And the other one is they charge in there and go, hey, great, what sign are you? Well, you gotta, if you're gonna be an ambassador for astronomy, you have to say, yeah, we diverged a couple of millennia ago. I'm kind of into more of the physics and astronomy thing. I believe in self-determination, these different things. But you know what? We do have a common bond in interest in planetary motion. And I've actually had some people that subscribe. So if you, instead of doing an insulting thing, go out there, reach out a little bit and explain things. And it can have some positive results. So educate people. Well, all that's to say that again, there's a reason you're sitting here and you're different than the average person. I mean, almost every kid I can imagine at some point gets a wobbly-legged little refractor, and they look through it. And most of the time, it gets relegated to the hall closet until it makes its preview at a garage sale, right? And we're hoping it's a Takahashi when we go to the garage sale. Usually it's not, though. But then you get another person, and they look through a telescope a couple of times. They may see the rings of Saturn, and they're hooked, and they become a naturalist of the night skies, and they end up joining us at venues like this. So what's the difference? We have run an article in the magazine called Star People that highlights different amateur astronomers, and we've done it since our very first issue and continue to present. I would always like to do that. I've always enjoyed it. What makes one person look through a telescope, see an uninteresting gray smudge, and another person look through it and they see photons have been traveling since dinosaurs roamed the earth, and holds the secrets to the universe and all these different mysteries and avenues to learning more about our universe. So what is the difference there? And there are some key differences, and through this and this series, as we've done this for 25 years, there's a couple of common bonds. One is they have some natural interest in the natural sciences, but the second thing is there's a lot that had certain early influences from some kind of a mentor, or somebody shared a view in an out-of-the-way place and it grabbed them. And so that's a topic I want to develop a little bit. And in my case, one of my earliest mentors is this woman, my grandmother. She's a Juilliard trained concert harpist and turned educator, and grandmother used every opportunity she could as an educational moment. And she literally, there was a time in my life I probably either go to prison or go to college, and she was the fork in the road. And I remember it very distinctly because I thought I was going to lose my life. When I was 8 years old, today they would have me on medication. Back then, you were an active child. So it's just different. Well, I was an active child doing what I do, and I was experimenting with spearfishing in her fish tank with a barbecue fork. So now grandmother's a serious woman. So this is how she reacted, and her reaction was so different than what I expected. I truly remember it to this day. And she bent down, and honestly, I was thinking, I'm losing my life. You know, even my little foggy 8-year-old mind was like, this isn't a good situation. I'm going to get my butt beat. She grabbed my chin, looked me in the eye, and said, Charles. Now, I knew this was a pay attention moment. She was a serious woman. She said, Charles. Because my only excuse that I offered to her was, I'm bored. Yeah, great excuse. So she says, Charles, boredom is for people who are unintelligent, unimaginative, or uninspired, and you are none of those things. Now, down the hall is a library full of books with the thoughts of some of the greatest minds that have ever lived. And outside is a world of nature that could fill 100 lifetimes with amazing and wonderment. She grabbed me by the hand, said, let's go discover something. It's like, wow. Powerful stuff. So she taught me the power of questions and discovery versus being bored, letting your mind just settle. She took me outside and she was a walking encyclopedia. She taught me biological names of different things. We walked down. She lived in Ham Harbor by the shore, and we go along with the seashells. She taught me the prehistoric history of the horseshoe crab. And she had a story for everything, but she didn't stop there. She encouraged me to ask questions. And then she asked me questions to make me think. She would ask me, Charles, do you think these two things are related? Why? How? Charles, what do you think that is? And she made me start to think, and she says, when we get back, let's go to the library and see if we can find the answer. So she didn't always just give me the answer. She taught me to ask questions and begin to formulate and logically think through and answer my own questions. That is huge. And like I say, that made a big dividing line. As a result of that, I became a reader, and I spent a lot of time in her library. Her library was one of those, I mean, it was a real library. It had one of those rolling ladders, which sometimes I like to roll the ladder. I would climb up and get the books, and I spent a lot of time reading. And I was introduced to some of the greatest minds who ever lived in that library. It became one of my favorite places on the face of the earth. And that walk was the first discovery walk of many that followed. And it was 5 years later, lost my grandmother, but not before we spent a lot of those discovery walks together. How many of you all are grandparents? Don't underestimate the impact you can have on your grandkids. Yeah. So that was my first mentor. And as a result of that, for the last 30 years, I have set a goal to read a minimum of 50 books a year, which sounds great. Once you start doing it, it's easy on a multiple disciplines. A couple years back, I read a book, more of a motivational type of book. And again, I don't read all just science or astronomy or physics. I read theology and philosophy. I like to kind of broaden my field. My education didn't stop when I left college, and I think that's a good way to approach life. So I came across this book, A More Beautiful Question, The Power of Inquiring to Spark Breakthrough Ideas by Warren Berger. And it harkened back to my grandmother and what she was trying to impress on me. And it also spoke to, in my mind, everything that science and astronomy, amateur astronomy, is about. And it was based around this quote from E.E. Cummings, the very last sentence of his book, simply called New Poems. Always the beautiful answer who asks a more beautiful question. Always the beautiful answer who asks a more beautiful question. Now, E.E. Cummings is kind of famous for, messing with grammar to make you think about things. And if you look, he inextricably combines the answer and another question. He puts the answer first, and then he introduces this unexpected pronoun, who. Who? The answer, the question, or the person asking the question. And as you think about it, his inference, and as Warren Berger expounds on that, is that our lives are defined by the questions that we ask. And each question that is answered leads to another question if we continue along and examine it properly. And of course, it's not just, hey, what'd you have for dinner last night doesn't qualify as a beautiful question, but he defines it as a beautiful question, an ambitious yet actionable question that can begin to shift the way we perceive or think about something. That's powerful. That is what science and astronomy is all about. It's what personal discovery should be all about. It's what education should be all about. And it's not a new thought. I mean, if you go back to Aristotle, it's the beginning of organized thought. This is a quote from Metaphysics. Those who wish to succeed must ask the right preliminary questions. So questioning and that answering questions, but that it should be self-directed is extremely critical. And my grandmother understood that. When I read this book, I'm like, she could have written this. She understood that you have to ask questions. You have to ask critical questions. You have to introduce critical thinking. And I think that is largely absent in the culture today. We want to tell them what it is, but we're not stopping asking questions. Well, so thinking about this applied to astronomy, you got this Messier 1, beautiful image by Tony Hallis. And we know if you start to research it at all, just, hey, what is the Crab Nebula? Well, you find out that it was actually recorded by the Chinese back in 1054. It's a supernova. And that supernova was so bright, it stayed in the sky. It was visible in the daytime for weeks. And that may lead to beautiful questions about, gosh, different cultures and how they record history or natural events. And that can lead you down one whole road. The other can, what about this thing? What is it? What causes it to illuminate? Why does it emit so powerfully in X-ray? And you can look at Chandra images and ask those questions. It's got a pulsar in there. Well, that gets really weird. So what is a pulsar? Well, it's a neutron star. And that may lead you into beautiful questions about physics. And you look at it as you get baryonic degradation, and where the intense pressures collapse the electrons into the nucleus and forms these things, these exotic objects, where we have a sun as big as our sun is. Imagine 1.5 times that mass compressed into 10 to 20 kilometers. So amazing, incredible thing. What's synchrotron radiation? Well, that will lead us to that, and that's a whole different branch. So there have been whole symposiums on this one object, and this is just the first object in a limited catalog of Charles Messier's non-comet images. And so it leads you into one thing and another as it goes on, and each answer leads to another beautiful question. And this one, M82. It's an active galaxy, not like a lot of them. You see this incredible outgassing. Well, what's an active galaxy? What other active galaxies are there? As we answer the question, we get more and more answers that lead to more beautiful questions, and we find out this is an incredible. The active regions in there are very unusual, and there are only a few of these galaxies that emit this powerfully in almost every part of the electromagnetic spectrum. And so that can lead into other things, the life of a star. What happens when stars are born? What caused it? Well, interaction with a nearby galaxy, and we can lead to gravitational waves and things that cause collapse in space. And there's no end to these things that lead from one object to another as we expand our understanding. And through all that, we begin to develop more of a sense of ourselves as well. And then we ask, well, where are these things happening here in our local neighborhood here in the Milky Way galaxy? Well, not nearly like that, and it's probably a good thing because life couldn't exist with that kind of activity. But in the core, you all probably seen it this week, beautiful, local, but in the trapezium there, get a big scope, and we can look into those areas where they're protostars, and you get this intense energy which is ripping the electrons off these different elements, and when they recombine, they give off packets of energy in the visible range. And that can lead you back into your, hey, the old physics or chemistry or something else, and I image this with narrowband filters, and I can not only combine it for a pretty picture, but I can actually look at, so what is the shape of the ionized oxygen versus the ionized hydrogen or the ionized sulfur? And you begin to this process of discovery that leads you to more beautiful questions. We got this one that's up a little bit above Omega, if you can ignore the beauty of Omega for a few minutes. Jump up there to this 5128. It's one of the most powerful radio emitters. Well, why does it emit powerful radio waves? There are more beautiful questions we ask. How can I measure the radio waves? It might lead you to an article in Amateur Astronomy and take an old satellite dish and build a radio telescope for yourself. All kinds of things. It's an elliptical galaxy, and it's kind of but it's an irregular elliptical. As you can see, it's kind of twisted. So what causes that? And that may lead you into more beautiful questions about the way they classify different galaxies. So what's an elliptical versus a spiral bar? And this beautiful object, one of my favorite visual as well as photographic, Thor's helmet, and it contains a very special star, WR7, which is a Wolf-Rayet star. It's a pre-supernova candidate. And everybody's been looking at Betelgeuse and noticing it's getting dimmer, and you probably read that they're wondering, will it go supernova? What's the difference between a Wolf-Rayet and that? And there are significant differences. Both of them possibly supernova remnants. What other objects have a Wolf-Rayet star? Where are they located? Well, the crescent does. So what's similar? What's different? Why do you got these wings? Why is it formed like it does? What other nebula have these things? So this man took it a little step further, and he took his amateur equipment and built a spectroscope out of it with just a few $100s worth of stuff and some software. And he actually wrote an article on measuring the spectral analysis of the terminal wind velocity on this in the Wolf-Rayet star in Thor's helmet. Wow. That's why the guy was mad at me at the amateur thing. These people are intellectually creative. So, and this one, anybody know what this one is? This is the wonder of wonders. Hard to find, but it's the double lens quasar. Quasars are not a visual like, wow, this is just an incredible object. When you see it, they're tough to find, but when you see it, and this one, the twin lens quasar, is 8.7 billion light years away. That's more than halfway back to the beginning of our universe. That's exciting stuff. But what's more exciting is 3.7 billion light years directly in front of it is a supermassive galaxy. And it is so massive, it actually warps time and space. And it splits this light as it travels around. There's 417 days of difference between those two light sources. And when you see that, you're seeing actual empirical evidence you can witness with your eye through your amateur telescope of Einstein's general theory of relativity. This is amazing stuff. This is incredible. And when you understand it and you engage your mind, it makes the hair stand up on your arm. Even though you're seeing two little specks, two little smudges. So we have to engage and ask more questions. But that can lead to to all the latest in physics theory. And so we got these two perspectives. My grandmother introduced me to this kind of questions and discovery. The other one is amusement. And think about the word. Muse, from the Latin to think, and a, the prefix, is without. So entertainment without thought. Now, I can entertain myself without thought plenty, but it shouldn't define my life, and it definitely shouldn't define our culture. And I'm afraid we're moving in that direction, where we're more about the amusement than we are about critical thinking and question and discovery. And this is something you see all the time. We live in this age of incredible technology, but diminishing sense of wonder and the ability to think critically. And you go out to a restaurant, and it's not just young people, and I've been guilty as well, but they're so plugged into it, their focus is there. Entire family or friends get together. They're getting together with each other, and they go out to eat, and then they're texting people who aren't there, missing the richer opportunity of the people that they're there. That's concerning a little bit. And it's not just the kids. I mean, the adults too. So we got to remember to engage. But guess what? We have the answer. And that's why I really encourage, and there's a number of you here that do a wonderful job of this, and my hat's off to you, and I encourage you to keep doing it, because I think it makes a huge impact. Teach people to ask beautiful questions. You got to show them stuff to get them out of the box a little bit. And so getting out there and not just showing them stuff, maybe ask them some stuff like my grandmother did. What do you think that is? Or give some information and get them to inquire as well. And I love this picture. It was on the cover. Richard Wright shot this. And what I like about it, I asked him, hey, did you pose those people? You looked at people in the background pointing up. He said, no, I just shot a picture of the girl with the telescope. And that made it even more special to me, because if you look in the back, you got one person who looked at something in the telescope, pointing out to another who's also pointing up, and the young kid, they're both telling the young kid about it. That's the power of getting people, opening their eyes to things they didn't see before, expand their awareness of what's about them, what's around them. And I do a lot of outreach at schools and basic science education. But some people say, well, I don't know enough to do that. Yes, you do. I just told you 25% of the people still think that there's a possibility that the sun revolves around the earth. You got that down, you got something to share with people. So get out there, show them what you can. And I'm usually in a light polluted parking lot at a school. Our teachers really need our assistance, because it's where the application, the applied part, is where you start that fusion process and get them going. They need to actually see, some craters on the moon. And yeah, you can't show them a lot of stuff from these parking lots, but you can show them a planet. You can show them the bands on Jupiter and the moons going around it. And it makes a huge impact. And about a little less than 4,000 people, and Randy, you probably smoked me big time. But yeah, get out there and show people some views. And this, like I say, the moon was just rising. It was low. It was horrible conditions, and they still were like, wow, as you tell them about the craters on the moon and how it tells a little bit about the history of the moon and the history of our planet. So you get out there and show them. Now, every once in a while you hit just one of those, you get a supernova, and this young lady was one, and I try and reward them, do something crazy, and obviously this is a Photoshop thing from down under in Australia, but I wanted to take a picture of her with a scope and dropped in a background and printed it out for her, because her first one showed up when she was in 4th grade. And she helped me out. She was one of those that really helped, and she actually, by the end of that, she was helping control the telescope and telling the kids, yeah, don't lean on it, don't move it. Yeah, and she was doing that, so she assisted. So the next one, when I did the next year, 5th grade, and she asked, hey, can I help you? So she helped me set up the telescopes. By the 3rd year, she had gotten her own telescope. She was setting that up and helped me do these outreach events. Well, she kept on going, started doing her own outreach, and she is now I guess a sophomore at Caltech. So, wow, sometimes you see one that takes off. So this is, and let's see if I can actually get this to do it. And this is, if it'll work with this video card, is horrible, but here is an event with some of the people at my local club. We got together for Mercury transit of the sun. You see, not perfect conditions, but nice thing about solar, you don't even need perfect conditions. We saw through the haze, but we're setting up, and you see all those students. We always take 10% of our profits from the magazine, put them back into public outreach, and we gave out over 1,000 solar glasses. They set up scaled, of our solar system, the different weighted buckets, what would this weigh on their plane. Just all kinds of things to engage the kids. We had a big, massive meteorite that Delani set up, and we had video presentations. We put on like a science fair for these kids. But I tell you, going outside the classroom, engaging in this stuff, getting them to look through an eyepiece made a huge impact with these kids. And we spent the, good 4 or 5 hours to get them through, but we marched through over 900 kids with the help of some of the people from the Astronomy Club as they go through right down to the little ankle biters, and they don't retain as much as the others, but you still got them. They're going, ooh, wow, yeah. And they love the little solar glasses. They can look at them. You got to explain the safety factors, but the teachers get involved, and guess what? Parents show up, and you get a chance to talk to the parents as well. So here we are packing up and heading off, exhausted, but very happy. So it was a great event, and there definitely is a changing demographic. We do some things. Celestron has been a great supporter of our public outreach. They donate telescopes to give away to kids at different things. And this was, I had three judges. They weren't blind, but they didn't know the kids, submitted essay contests, and they had to do an observing report on some different things. And so we didn't know who the kids were, but 8 of the 10 kids that won scopes and different stuff like that were girls. So the whole thing with the boy dominated, that's not, I'm worried about the boy, honestly, and I say that, I'm worried about the boys at this point. I don't like to see any kids. It shouldn't be a gender thing, but females are definitely engaged at this point. Very good. But yeah, let's not leave the boys behind either. So, but anyway, anything you do contribute. This young lady, a number of years ago, Pranvera Hyseni, yeah, she was virtually unknown. We featured her in Star People because we thought what she was doing in Kosovo was very interesting. Since then, she has developed, now that she's building an observatory in Kosovo, she came over here and spoke around the country, find people to contribute. And so she's a dynamo. That's just making a difference in a country that doesn't have a lot of resources. I get back to Julia Mariana. She's got her own organization. Like I say, she wants to be a Carl Sagan, and it's very possible. And I would be negligent if I didn't remember some of the people who made impact, certainly on me and larger crowds who have passed on. Maybe I remember Walter Scott Houston and his articles. I mean, it's one of the things, even as a kid, that got me interested. And Carl Sagan, I think anybody, he was, to me, one of the great communicators, and his Cosmos, original Cosmos series, to me was just phenomenal. And also fiction. A lot of us come from science fiction that leads us, and good science fiction is based on science, and it's expanding on that some. Clyde Tombaugh started as an amateur, remember it, and I think it's coming up on an anniversary of his discovery of Pluto. Is that correct? I think so. Billy Dodd, some of you may know him, others may not, but he started Chiefland Astronomy Village. You may know somebody like him. He started the astronomy outreach for your club, but he actually bought this land, and Chiefland is a very vibrant astronomy community to this day because of it. And Tom Clark's in there with Casper and Bill Williams, but great friends and a great community we developed around this. From Miami, I grew up in Miami. Jack Horkheimer, anybody remember him? Oh, yeah. Yeah. Stargazer. Tom Johnson, why did I mention him? He developed the folded optics that made astronomy and longer focal lengths available and affordable to people, and that's a big deal. If you can't afford it, our hobby can be pretty expensive on the one extreme, so it's great when we can do things, get people involved. Tammy Plotner, may not know, personal friend, even when she was very sick, she was a gracious host. She was a writer, contributor, and great promoter of astronomy. John Dobson, our publication wouldn't exist without John Dobson. His Sidewalk Astronomy launched a whole new aspect to public outreach. Don Parker, certainly those of you in this area know Don Parker. Incredible planetary imager, but those who don't know him may not realize he also used to sketch, and he sketched with such accuracy that it had scientific merit, and they study him to this day to follow patterns. So Barlow Bob, guy who started the Neef Solar Star Party, lost him a couple years ago. John Davis, who writes for us, we still have some of his articles that we're publishing in there. Great author and communicator. Tippy Dioria, the founder of our feast here at Winter Star Party. And Barbara Wilson, just recently, incredible observer, deep sky, really pushed the limits of what you could see. And so these are all people that have had their impact on this community and well beyond our community. So encourage you, get involved, be one of those people who makes a difference, that pushes the envelope a little bit, continues our hobby. But I always finish with this, and this is the 10 commands for amateur astronomers. So, thou shalt have no white light before thee, behind thee, or the side of thee, whilst sharing the night sky with the fellow stargazers. Most of us are good with that one. Thou shalt not love thy telescope more than thy spouse or thy children, as much as maybe, but not more. Thou shalt not covet thy neighbor's telescope unless it exceeds an aperture and electronics twice that of your current, then it's okay. Thou shalt not read amateur astronomy or sky and telescope on company time, for your employee makes it possible to continue in your astro pursuits. Thou shalt have at least 2 telescopes, so as to keep thy spouse interested when the same accompanies thee under dark night skies or bright sunny days. Then thou shalt not allow either thy sons or daughters to get married during the holy days of TSP, WSP, Okie-Tex, Starfest, any other. It's a big no-no. Thou shalt not reveal to thy spouse, this one's very important, the cost of thy telescope, imaging equipment, only the individual components, and thou shalt be done with great infrequency, is highly recommended. I did learn something from my wife. You know, she likes, kind of like I like eyepieces, she likes watches, just really likes watches. And so I thought, oh, that's a nice watch. You get that? Oh, I've had that for a while. So I think she like put it up for a bit, and then I noticed it, and yeah. So I said, well, that'll work for eyepieces too. Oh, where'd you get that big eyepiece? Oh, I've had it for a while. Just sitting in the garage for 2 months. You know, it's like, so just be smart. We don't want marital inharmony. So thou shalt not buy thy spouse any lenses, filters, dew shields, maps, charts, or other necessities for Christmas, anniversaries, birthdays, unless thy spouse needs them for their own telescope. Yeah, boy, that's incredible eyepiece. Too bad you don't have a telescope. Okay, I can keep you company for you. Thou shalt not deceive thy spouse into thinking you're taking them for a romantic Saturday night drive, when indeed you're headed to a dark sky site. That was big no-no. Thou shalt not store thy telescope in thy living room, dining room, or bedroom, lest thou be sleeping with it full time. I did. One of my friends, I walked in his door, and right in the foyer there was this big, you know, AP 1200 with this big scope, and I was like, the spouse wasn't happy with it. Loved the scope, loved the man. Get out of here. So, addenda, verily observe or image, not through thy neighbor's AP or Arcos or Dob of Goliath, lest they be utterly consumed by the lust of apple fever, and thy brain and thy bank account shall shrivel like branches in a flame. So, be very cautious. Thou shalt subscribe to Amateur Astronomy and record and contribute your observing reports and images on a regular basis, that others may be blessed with your knowledge and your passion. But most important of all, I mean, you have some fun with this, but please continue to ask more beautiful questions. Don't let yourself just get numb to the whole thing. I get people all the time that say, yeah, I got a little bored with astronomy. I've seen everything, imaged everything. I'm like, really? I feel like my grandmother. I grab them by the chin, look them in the eye, and say, yeah, boredom is for people that are unintelligent, unimaginative, or uninspired. And I don't think they're unintelligent or unimaginative, sometimes uninspired. That's why I encourage myself and make myself read 50 books a year. Readers, you got to keep the stimulus coming in. Get around other people. What are they doing? What are they looking at? What do they know? It stimulates the gray cell. Pass on your enthusiasm for astronomy to others. Encourage them to ask beautiful questions. Make sure, again, get them to ask questions. Don't just always tell them. Help that person who is a step or so behind you to advance to the next level. You don't have to be the wizard. You don't have to be an expert. If you know something that they don't know, share it with them. This hobby is wonderful that way. I've never been involved in anything where people have been so kind, so generous, so sharing of what they know and their equipment. So go out tonight and discover something. Stop and look up, and don't forget to just wonder. And then ask yourself a question. And then engage with your eyepiece or your CCD to find the answer. Anyway, thank you very much. I appreciate you having me here. I'm enjoying Winter Star Party very much.
have another prize to give out, and Olivia's going to select a new number. Olivia?
323.
323, Pat. Give him a prize, 323.
Number 323, Adam Toder. You've won a Celestron Power Tank Glow and 2 tickets to the 2022 Winter Star Party and a gift certificate from Infinity's T-shirts. Have a good time.
Hey, hey, hey! It's time for some of those world-famous Star Party brownies from Micki's Kitchen. This one's going to be a good time. Tippy D'Oria doing his presentation on how to gauge astronomical distances. Watch for the toilet paper.
Good afternoon, everybody. I'm here to introduce Tippy D'Oria, founding father of the Winter Star Party, and acting. I've deputized him for some activities, but Tippy's the founder of Winter Star Party, which is sponsored by the Southern Cross Astronomical Society, and has been the chairman of this Star Party for 13 years, over its 22 years. Is it 22 years? Yeah, it's 22 years. Did we count 98 as a year?
Yes.
We did count that, okay. And not 98, 99.
99. We just held it chief.
Okay. Tippy received recognition for his contributions to amateur astronomy, as he was honored the International Astronomical Union when an asteroid was given the name 11378 D'Oria. Tippy is a noted astrophotographer who used cold camera photography for his work and has taught creative photography and darkroom techniques at college level. Tippy is a writer and international lecturer, as well as an avid volcano hunter. He's contributed to the section on darkroom techniques for the book Introduction to Observing and Photographing the Solar System, as well as co-authoring with Vic Menard Perspectives on Collimation Principles and Procedures. So here's Tippy.
Thank you, Tim. Well, the talk that I'm going to do tonight is more or less dedicated to newcomers to astronomy. You old-timers already know about most of this stuff, but you might learn a little bit more than that you didn't know before. This is a new way to measure astronomical distances. Now, this is going to work this way, I guess, right? Yeah. Okay. They're going to have flyovers coming in. Okay, as we look at the planets of the night sky, and the planets, we can't help but wonder about their distances from us and their sizes. The answers to these questions of distance and size are just too large to be meaningful. They're beyond our experience. Two examples of this would be our moon. It's the closest astronomical satellite to our planet Earth. And it's only some 2,160 miles in diameter. Its average distance from us is a mere 238,585 miles, 855 miles, which is nothing in astronomical distances. Or a red giant like Betelgeuse in Orion. It has a diameter larger than Earth's orbit around the Sun. It has a diameter of 700 million miles and is bigger than our Sun by 700 to 900 times. Yet, it's 17,000 times brighter than our Sun and lies at a distance of 520 light years away from us. Now, in order to develop a feeling for the distances and sizes involved in astronomy, we're going to take an imaginary trip from our local star, the Sun, out into space until we reach one of the nearest stars in the sky. We're going to go to Sirius. Whoops. Now, Sirius is 8.7 light years away, And we take this journey at the imaginary speed of light, which is the fastest speed theoretically possible to go. Now, before we learn, we have to learn, we all know the units of the inch, the foot, the yard, and the mile. But for astronomical units, we need to learn two new units. The astronomical unit, which is the distance the Earth is from the Sun, and Pluto is 40 astronomical units from the Sun, which makes our solar system have a diameter of 80 astronomical units. Now, this represents, an astronomical unit represents approximately 93 million miles, or 8 light minutes. That is the time it takes the light to get from the Sun to the Earth, 8 light minutes. Now, a light year. All radiant energy travels at the same velocity, commonly called the speed of light. The speed of light is 186,000 miles per second. It's not a measure of time, but a measure of distance. And a light year covers approximately 6 trillion miles. That's the distance that it takes 1 year. Now, the irony of it all, to give you an idea how this works, ironically, there are 63,360 inches in a mile. And there's 63,240 astronomical units in a light year. So let's make a scale model of our solar system using that figure. We have 1 inch, then could be 1 astronomical unit. So if we took the Sun here, 1 inch away would be 1 astronomical unit. Some 40 inches away would be our outermost planet, Pluto. On that scale, the nearest star to us would be 4.5 miles down the road, to give you an idea how that works. With the Earth 1 inch away, Pluto would be 40 inches away, the nearest star would be 4.5 miles away. Now, finally, let us imagine our several hundred billion stars in our galaxy with their enormous separations arranged in space as a great star city that measures around a large, like a pizza, a large flattened cloud that measures some 100,000 light years across and some 10,000 light years thick in the core. This wheel is our Milky Way galaxy, and here's about where we live, which would be right out in about 2/3 of the way out there like that. Okay. This is our solar system. Our sun and solar system lie about 30,000 light years from the center of the galaxy. Even if you were driving a race car at 100 miles an hour, it would take more time than the entire age of the galaxy, some 12 billion years, to reach the galactic center. In fact, it would take a total of 201 billion years to drive to our galaxy center. Can you imagine what the gas bill on your car would be there? So let us begin our journey to Sirius. Now, we've come up with this very special astronomical measuring paper. This was developed by myself and Dr. Don Parker in Miami. And let me you laugh, but this is very scientific. This is not what it appears to be. But we're going to scale everything down. This paper is going to be measured, each sheet of this paper is going to measure 1 million miles. That's 1 million miles. We call that the Dioria. The Dioria equals 1 million miles. Now, what we call this stellar, heliocentric, illustration, tissue, or because we make acronyms out of everything, we could just do it like that. Now, how many sheets of this paper do you think it's going to take to get us to Sirius? I'm going to be using some slide notes here, and we're going to scale this whole thing down to this size. So if the sun, which measures a diameter of about 865,000 miles, would be about the size of a softball, so it would be a little bit smaller than this. So using the stellar heliocentric illustration tissue, we're going to scale down the planets of our solar system down to comparative sizes. Now, those are the sizes that they relate to each other. We're going to go, okay. Our sun begins at a bright yellow-white subject size of a softball on our scale using this stellar heliocentric illustration tissue. This is the sun. It's composed predominantly of hydrogen and helium with a ratio of about 3 to 1. And it generates its energy by nuclear fusion processes. From the center of the sun, the temperature falls from about 15 million degrees Kelvin to 6,000 Kelvin. With a diameter of 865,000 miles, it's somewhat smaller than one sheet of paper. And the sun lies in the center of our solar system. Our first encounter after leaving the sun takes us 3 minutes and 36 sheets of paper. I've got that measured out. That's 36 sheets of paper. Don't laugh at me, because you don't know what's coming. And that is going to bring us out to, okay, this is crater marked planet Mercury. Mercury is the closest planet to the sun. It is an arid, airless world with a meteorite battered surface baked to above the melting point of lead at midday, about 800 degrees Fahrenheit, and cooled to a bitter cold of minus 300 degrees Fahrenheit at night. This temperature spread is due to an extremely thin atmosphere. Mercury could never have supported life and more closely resembles our moon and any of the other planets. It rotates on its axis once every 59 days and travels about 30 miles per second in its orbit around the sun. A Mercurian day, sunrise to sunset, is equal to 59 Earth days, and a year on Mercury is equal to 89 of our days. On our scale, the 3,000-mile diameter of Mercury shrinks to the size of a hole made by a needle. Now we have to tear off 31 more sheets. And that is going to bring us to Venus. We arrive at the second planet after 6 minutes and 67 sheets of stellar heliocentric illustration tissue. This cloud-covered Venus is the only world in the solar system that closely resembles Earth than any other planet. At a time approaching as close as 40 million kilometers. It has a diameter of 7,500 miles, and its day is equal to 243 days on Earth, while its year is equal to 225 of our days. This would make a Venusian year shorter than a Venusian day. The planet is covered with a dense white cloudy atmosphere that is almost all carbon dioxide and conceals whatever is below it. The clouds of this planet consist of tiny droplets of sulfuric acid particles. This thick atmosphere accounts for its high surface temperature of about 800 degrees Fahrenheit. Both day and night size of the planet. This is the greenhouse effect. Venus is the size of the thickness of a wire used to make a paper clip on our scale. So now, to get to the Earth, which is 93 million miles, we have to tear off another 26 sheets. 12, 24, and 2. Yeah. You wait. Okay. We passed the 7,900 mile diameter home planet, 8 minutes, 93 million miles, or 93 sheets of stellar heliocentric tissue. And this has a substantial atmosphere, mainly of nitrogen and oxygen, for which we appreciate greatly. 2/3 of the planet is covered by water, and the Earth's surface transfers to the atmosphere an amount of energy equal to the amount that it absorbs. The Earth travels about 600 million miles in its annual orbit around the Sun. After 4.6 billion years, the Earth's internal heat is still a source of mechanical power, producing earthquakes and volcanic eruptions, raising mountains and moving continent-sized blocks about its surface. This is I didn't do that. This volcano, this is the Arenal volcano down in Costa Rica. I photographed that particular photograph made the cover of Parade magazine. That was a great volcano. Okay, now we have to, like Earth, Venus like Earth is the size of a wire paper clip. We tear off another 48 sheets. More. Okay. Okay, and I apologize to Don Parker. I'm apologizing to you for this, because this is the way everybody else shows it, but really this is actually upside down. This is the South Pole, that's north, but we always show it upside down, the Alpo, and this is not according to Alpo. So I apologize, Don. We arrive at Mars after 13 minutes and 141 sheets of paper. With a diameter of 4,200 miles, Mars is a little larger than 1/2 the size of the Earth and travels about 15 miles per second in its orbit above and around the Sun. While a day on Mars is very nearly the same as on Earth, 24 hours and 37 minutes, a year on Mars is almost twice as long. A year on Mars lasts 687 of our days. Mars has a thin atmosphere that consists of 95% carbon dioxide and about 2.7% nitrogen and some argon. There's no evidence of liquid water on Mars, although some planetary scientists believe that there's water in the form of permafrost a few meters below the surface. Water was once probably abundant enough on Mars to leave major structures on the planet resembling riverbeds, likely carved during the planet's early history. Winds in the Martian atmosphere reach speeds exceeding 186 miles an hour and create vast dust storms that can completely envelope the planet for weeks on end. It is about the thickness of a staple on our scale. Now we have to tear off another 342 sheets for a distance of 483 million miles to get to Jupiter. Now normally, at this time I have help from my friend Mr. Biscuits. Mr. Biscuits goes with me everywhere. I carry him in my camera bag, but he was tired. He was up observing last night and can't do it. So I'm going to ask for some help from the audience. Now, ye who laugh. First, you just take this and you just reel this off, and don't be ashamed to give it to somebody else. And they in turn can give it to somebody else, and I'll tell you when to stop. We're going at the speed of light, so don't dally. Just pass it around. I'll tell you when to stop. Just hand it back to the next guy. Let him take it and go with it. This lecture lasts only as long as it takes to get this stuff out. Don't be bashful, don't be bashful. You laughed at me.
Wait till we get serious.
Oh, yeah. You have no idea how this is going to go. We just keep going. You go. Keep going. Keep going. No, that's all right. I'll be bringing some to you guys too. Just let it pile up over there. You guys will get it. Keep getting it. Keep taking it. Okay. Now we can stop it right there. See, now you guys don't look so pretty either. Right. Now, I did forget to mention that we're running low on toilet paper, and I borrowed this out of the thing, so we're going to have to roll this all back up, so don't tear it up too small. Now, we can go to the next one. This planet with a diameter of 88,700 miles is the solar system's largest planet. It's equal to 1,318 Earths in bulk, and it'll appear as a striped sphere slightly larger than the hole in a phonograph record, for those of you that remember phonograph records. Jupiter has an extremely rapid rate of rotation. And when you look at Jupiter, a lot of the images you see in Jupiter, you'll see it will appear to be bulging in the center, and that's due to that rapid rotation, by the way. Jupiter's day is only 9 hours and 50 minutes long, and its speed at the equator of 28,000 miles an hour causes the appearance of bulging at the equator. It takes almost 12 of our years for Jupiter to make one complete circuit of the sun. An interesting thing about the 9 hours and 50 minutes that Jupiter rotates, when Shoemaker-Levy 9, the comet that fragmented into 21 pieces, as it crashed into the planet, it had stretched out to a period of time so that when the impacts took place, they took place at 10 hours apart. So when one impact would hit, 9 hours, 57 minutes would already come around, and right behind it would hit the next fragment. And they came in one right after the other. That's what made that. So it was really, really kind of neat. And Dr. Don Parker, who's sitting back there, was one of the ones, very few people was fortunate enough to, I think he photographed every impact, didn't you, Don? The atmosphere on Jupiter appears to be methane and ammonia. Yeah. The atmosphere on Jupiter appears to be methane and ammonia, not unlike Jack Newton's house after a bowl of Alice's chili. It's assumed that a large fraction of hydrogen and helium must be present also, as well as water. The temperature of the tops of the clouds may be about minus 260 degrees. The windswept visible surface of Jupiter is constantly changing. This is the Great Red Spot, a salmon-colored oval vortex whose hue is possibly due to organic-like compounds that are constantly spewed from some heated atmospheric source below, and is perhaps the longest-lived structure on the visible surface of Jupiter. Or perhaps there's no surface at all. For there's evidence for considering Jupiter to be almost entirely liquid hydrogen. Finger went to sleep. The first few planets that we went past are solid planets too, by the way. We're now entering into the giant gas giants. These are gas giants. It's interesting to note here that Voyager 2, launched in 1977, took 2 years to reach Jupiter. At the speed of light, it would have taken 35 minutes. But now, we have to tear off. You ready? Ready to fly? We've got to go another 403 sheets. So another 403 sheets have to come off and be passed around to make my audience look absolutely ridiculous.
They're not getting any action back there.
Give some to Parker back there.
They're wiped out back there.
Yeah. Keep going. We're supposed to be going at the speed of light.
Well, we got 35 minutes then, right?
Okay, we can stop there for the moment. Okay. Now that's the red spot. Okay. We arrive at, now we can go to Saturn. This thing's not working. We arrive at the last of the planets readily visible with the naked eye, ring Saturn. It's almost twice as far from the Sun as Jupiter, almost 900 million miles. Saturn's rings consist of billions of particles that range in size from microscopic specks to mountains kilometers across. The reason rings is plural and not singular is that gaps and brightnesses define hundreds of distinct rings. I couldn't tell you from memory now what occultation I saw several years ago, but my wife and I, Pat, set up a 12-inch scope in our front yard when Saturn occulted a star. I can't remember what star it was. Yeah, it was absolutely spectacular because as the ring system passed over the star, you could see the star dimming, getting brighter, and dimming and getting brighter due to the thickness and the density of the ring. It was really slick to see that. Saturn's day averages 10 hours and 39 minutes, but its year is almost 30 of our years. It has an atmosphere much like Jupiter, except its temperature at the top of its cloud layer is at least 100 degrees colder. It has a belt system like Jupiter's, but it's much less active. The second largest planet has a diameter of 74,000 miles, or on our scale, the thickness of a pencil. Now, assuming our astronomical illustration tissue is a standard 1,000 sheet roll, we find ourselves passing Uranus. I actually got kicked, I got to tell you a quick story. I actually got kicked off of a bulletin board for saying Uranus. We were trying to get somebody, we were spelling it phonetically, and I said it's Uranus. And the guy that was in charge of the group says, you can't use that kind of language here. I said, it's not language, it's the name of the planet. He said, change it. And I said, I can't change the name of a planet just to please you. This is the way it is. And he locked me out. I couldn't talk on there. That was on Genie years ago, for those of you who remember Genie. I couldn't believe it. The guy was a brilliant man, I suppose. Okay. Now we have to finish. This is going to take a trip now. This is going to be a trip now. We have to finish this. So get going, because we're going to finish this roll plus 783 more sheets, which is going to bring us. Now, that would mean that this first roll was 1 billion miles. So we're going to finish that one roll, and I happen to have, oh yeah, I just happen to have there you go. Get flying. That's the way. That's the way. Get it going. Now, by taking off that first roll plus 783 sheets is going to make the distance to Uranus 1,783,000,000 miles. Can you imagine trying to figure this out on a bathroom on a Sunday morning sometimes? Oh, I went all the way to Mars today.
Like you did. Maybe it's the speaker now. What happened?
I don't know what. We didn't fly past that. We got to back up. We got out there. You went too far. Yeah, there you go. Keep going, guys. Keep going. This works better when you got a bigger audience. Look at Mo. Mo's seen this talk before. Look at that. Show him, Mo. Mo. We're almost there. Okay. Nope, a little more, a little more. Okay, you can take a rest there. Okay, we reached the planet Uranus. It's taken us 2 hours and 40 minutes to reach this shoelace hole-sized world, whose real diameter is 32,000 miles. It took Voyager 2 9 years to make this journey. The planet Uranus was apparently unknown until 1781, when it was accidentally discovered by Sir William Herschel with a 6-inch reflecting telescope. Uranus is in a forbiddingly cold place with temperatures around minus 300 degrees. It takes 84 years to make its journey around the sun, and its day is about 16.8 hours long. How do we get up there to Neptune already? We got back up. Yep. Uranus is tipped over. Its north pole lies 98 degrees from being directly up and down in its orbit plane. Thus, its seasons are extreme. When the sun sets at the North Pole, it stays up. When the sun rises at the North Pole, it stays up for 42 years, and then sets, and the North Pole will be in darkness in winter for the next 42 years. Okay, we continue our journey now from this gas giant out to another one. Oh, I didn't mark how. Oh, this is the size of a shoelace. It's about 32,000 miles. So now we got to strip it out. We're going to peel this off, finish this roll, plus oh yes. We're going to finish this roll. I have a feeling they're passing it all around and running it right back up to me. But we have to peel off.
Well, somebody's got to clean it up.
Yeah. Well, I'll end up cleaning up. We finished that roll, plus 792 more sheets, which is going to bring us to 2,793,000,000 miles to get to Neptune. My pilot's getting tired. You're doing a good job, though. How did Patty get out of that? She... Yeah. Get up here. Okay, we got to get going.
We did that guy's house down the street when I was a kid.
I bet he loved you. Okay, we got to keep going. This is giving you an idea. We have to keep going, keep going, keep going. Just okay, you can, when you get to there, you can stop. Okay. Now, that brings us to the planet Neptune. We've gone now 2 rolls, 792 sheets. That's 2,792,000,000 miles from the Sun to the planet Neptune. Jupiter, Saturn, Uranus and Neptune are rather similar in the sense that the interiors consist mainly of hydrogen and helium, and their atmosphere consists of these same elements and simple compounds of hydrogen. Discovered in 1846, Neptune, whose diameter is 31,000 miles, is a virtual twin of Uranus and will be passed some 4 hours and 10 minutes after leaving the softball-sized sun. Neptune's day is about 8 hours long, and it circles the sun in 165 years in a nearly circular orbit. Now, this is the last known planet that we encountered defies the outer reaches of our known solar system. With a travel time of 5 hours and 30 minutes and a distance of 3 rolls plus 675 sheets. So we have to finish this roll. We're almost there, folks. Get this one going. We're almost home.
Well, not with that other new planet that they just...
Well, we're gonna. Yeah.
The warrior princess. A rocket just flames out.
See, we're right now we have 9 known planets. This other one hasn't been official yet. The Astronomical Union hasn't declared so. So we'll get this out, and that'll get us to, I'm sure, don't break the chain. Whoop.
Didn't you know that there's people in Africa who have been killed in it?
Well, we can mail it to them. It's amazing because when I first put this talk together, it occurred to me that when we get to this point, I never forgot how far away Pluto was. I always said, well, if it goes through 3 rolls of toilet paper plus 675 sheets, it's 3,675,000,000 miles. It's one of the ones I remembered. So let's see here. How we're getting there. Okay. Now don't advance yet. Now we're okay. We finished 3 rolls, 675 sheets, and we finally reached Pluto. Pluto was discovered in 1930 by the late Clyde Tombaugh at the Lowell Observatory in Flagstaff, Arizona. Up until June 1988, Pluto was thought to have no atmosphere. At that time, using a 30-inch telescope in an airplane at 42,000 feet, observers timing an occultation of the planet revealed that the star faded out. Instead of just blinking out right away, it faded out when it went out and then faded back in, indicating an atmosphere around Pluto. Pluto has a temperature of about minus 350 degrees. Pluto and its moon Charon are most certainly balls of ice and most likely water, methane, and ammonia. Astronomers estimate the size of about 2,000 miles, making it a thin, pinhole-sized sphere, even smaller than Mercury or Mars. It's about the size of our moon. Its average distance, it would take Pluto 248 years to go around the sun. Besides being the solar system's smallest planet, Pluto is different from the other 8 in almost every aspect. Its unique characteristics include its orbit, which is relatively higher inclined, and just where such a freak fits into the solar system's origin and evolution is unknown. There are no known photographs to show what Pluto really looks like, but I just received this Hubble Space Telescope image that Jack Newton and his computer enhanced to show its amazing detail. So that's what Pluto really looks like. Okay, Now we're going to start on the longest leg of our journey to Sirius, one of the closest stars to the Earth that we can see from our location. This part of the trip will take us almost 14,000 times the distance between Pluto and our Sun. It'll appear slightly smaller than a volleyball and require a total travel time of 8 years and 219 days to get there. At a cost of about $2 a 4-pack, we have just explored the solar system for less than $2. But to continue our trip, we would need a large storage warehouse to finish demonstrating this stellar journey, as it would require an additional 50,640 rolls of stellar heliocentric illustration tissue at a cost of about $28,000. Stacked one on the other, they would reach a height of 3.5 miles. And rolled end to end, the sheets would stretch 3,600 miles. On our scale, if the Sun was a softball here at the Winter Star Party, Sirius, the nearby volleyball-sized star, would be floating in the blue waters of the Pacific Ocean some 600 miles off the California coast. So I hope that this demonstration has given you some idea of our astronomical distances. Thank you. Now you know what's kind of neat?
And for the vendor award.
Yeah, well, I see this not only hit it, but I got a bag that I can put all the stuff in so we can clean it right up. Oh, Don said he'd re-roll it later.
There you go.
Oh, thank you, my friend.
Check this out.
I saw it.
Oh, you did?
You showed me the other night.
Oh, I showed it to you.
This is with a certificate. Ah, that's absolutely gorgeous. That is so beautiful. I've always wanted one of these damn things. They're just absolutely magnificent.
Go to Barry and let him know.
Did I got it?
Yeah,
Okay.
let him know what you think.
Oh, absolutely.
Yeah, that way it makes him feel good.
I will do that. I will make sure I do that.
Time for another drawing. Olivia?
24.
24. Pat, give number 24 a good one. Well, they're all good.
Number 24, Gustavo Cecchi. You've won Lunt Engineering's Astro and Yachting Binoculars 7x50 Magnesium. Nice product. Hope you enjoy it.
All right, guys, thank you for watching. We hope you enjoyed day number 1.
I'd like to thank our sponsors for providing us all the great door prizes.
Join us tomorrow night, same time, same channel.
The Southern Cross Astronomical Society of Miami, Florida is proud to present the 2021 Winter Star Party Virtual Edition, February 8th through the 11th. Because of COVID, we will not be able to get together in person this year, but we won't let that stop us from getting together online with old friends and make some new ones. There will be all new presentations about double stars, astroarchaeology, Mars exploration, and more. Enjoy classic videos from past winter star parties by Tippy D'Oria, Dr. Mike Reynolds, John Dobson, and more. Then join us February 8th through the 11th from 7 to 11 p.m. Eastern Standard Time on www.explorescientific.com/Winter Star Party. Mark your calendar. See you there.